Okay, great. Yeah, let's get started. Maybe some other people are still finding their way to this room. It was not that easy. Have you guys ever had a class here before? No? Yeah, they assigned this because it's one of the video conferencing rooms that's capable of recording. It's actually a nice classroom. Maybe I'll request it in the future also. Okay, let's get started. We'll continue from yesterday. Yesterday we actually covered a lot, and you guys were engaged. That's good. I'd like to keep it that way, keep being engaged. That's the best way you can learn in this class, I think. Today we'll continue with some more fundamentals, and we'll start the memory hierarchy. As I mentioned, we're going to focus a lot on memory hierarchy to begin with in this course. So this is the agenda I have for today. We'll finish up some logistics from the last lecture. We'll talk a little bit more about why study computer architecture, because I think that's important, especially knowing where computer architecture fits in the field of computer science and engineering today. We'll talk a little bit more on fundamental concepts and hopefully cover memory hierarchy and caches. It's an aggressive agenda, but we'll see how far we can get to. We're not in a rush to finish all of it. Okay? I guess ideally we will need to close those windows, but I think I like the natural sunlight here. Okay, so takeaway from lecture 1. I've given you 3 examples in lecture 1. Remember, memory performance attacks, RAIDer, refresh problem in DRAM, and rowhammer. They all showed that you need to break the abstraction layers between both components and transformation hierarchy levels. And you need to know what's underneath. And that enabled you to understand and solve problems, whether the problem is memory interference, DRAM refresh, or some failure mechanism in DRAM that no one has ever seen before. You can only find those out if you break those. So this course will continue to do that going forward. There's a little sound. Maybe I'm too picky on this. I think maybe I'll turn off my cell phone. That's another. I hear some static. Let's do the airplane mode. Okay. And again, as a review, the major high-level goals of this course, we'd like to understand the principles and the precedents in computer architecture. And based on such understanding, hopefully you will, by the end of the course, be enabled to evaluate the trade-offs of different designs and ideas, to enable and develop principal designs, and develop novel, out-of-the-box designs. That's the goal in the end. I don't expect you to do that right now, but it's good to start thinking new ideas, because whenever you have some problem, it's always good to start thinking about different ideas from what we've seen. And we will see. And the focus is on really principles, precedents, and how to use them for new designs. Just a note, I said this also in digital design, and I always say this in my courses. This course might seem like it's only computer hardware, but it's not really true, in my opinion. You will be more capable if you master both hardware and software and the interface between them. This course is really about the interface and how to merge hardware and the software together. Because hardware and software changes over time, right? I think I'll pick on Google's tensor processing unit again. People were doing that in software for a long time, right? But they decided to move to hardware. And if you know both of them, you can make that trade-off much more easily, and you can actually navigate that space of high-performance, energy-efficient computing. Because in the end, you can implement anything you implement in software, also in hardware, and vice versa. Of course, you need some basic hardware to execute things. But this is a very malleable trade-off between hardware and software. And over the decades, this trade-off has shifted. We have a lot of accelerators right now. People do video encoding in hardware, for example, whereas they used to do it in software. But if you want efficiency, you need to do it in hardware. Okay, and you can develop better software if you understand the hardware. Even if you're not designing hardware, you can develop much better software if you understand it. And hopefully this will be clear in some of the examples that we give today, later in caches, for example. And also you can design better hardware if you understand the software. It goes both ways. If you understand what requirements the software has, you can design it much better, what bottlenecks it exercises. Okay, and you can also design a better computing system if you actually understand both. And that's the eventual goal of the course, so that you can understand both and you can design a much better computing platform. In the end, computing is not about hardware or software only. It's really about designing the complete solution to actually solve a problem, right? So this course covers the hardware-software interface and microarchitecture. And we will focus on the trade-offs and how they affect software. Are you hearing the sound also? Yes, it's annoying, right? So how do we fix that problem, you think? I think I don't need to, but for recording. Yeah, that's what I was going to look at also. Any idea how? On the screen. Microphone, yes. System volume. Okay. I reduced both. Oh, I shouldn't. Okay, I see. So system volume is lower, microphone is higher, but I still hear it. Okay, microphone is lower. It's better, right? No? It's not? It sounds better right now. I don't hear it. Maybe I'm not sensitive enough. A little bit. Okay, reduce the microphone a little bit more. How about this? Is it better? I'm moving around. It feels better now. Okay. Sorry about that. That was the problem, apparently. Okay, there's a problem now. You solved the problem. There you go. And you need to know the interface to solve the problem. I don't know if this was a hardware solution or a software solution, but it looks like a software solution to me. Okay, anyway, jokes aside. So what do I expect from you? We didn't cover this yesterday, but required background digital circuits course. How many of you have taken it again? All of you almost, that's good. So if you haven't, you should probably brush up a little bit on some things, but as long as you have this open mind and you're willing to take in many exciting concepts, you'll be okay, I think, if you have some background in computing, since you're master's level students or late bachelor's level students. And programming, and all of you know programming, so that's needed also. Learn the material thoroughly. I think do the readings, attend the lectures, do the exercises, do the labs. That's how you can get the best out of the course. This will be a hard but fun and informative course, like all of my courses, I'd like to believe. But it should be fun, I think. Ask questions, please do that. And yesterday was very good, I think. Please continue to ask questions, take notes, and participate. Even though the slides are and the videos are online, it's always more efficient. I find it more efficient to take notes, actually, because I'm not going to go back and watch all of the videos again, right? Perform the assigned readings. There will be some readings that we assign. Some of them are optional. Some of them are required. Some of them you will do reviews for, which we will also talk about, how to do critical reviews for works. I don't expect you to do all of the readings that we discuss, because a lot of them are really optional, but the more you do, the better, the more you will get out of the course. I think even though things are recorded, I would rather have people coming to class and participating, asking questions, because that's a much nicer way of learning than just watching lectures. Starting early will be important for assignments. And if you want feedback, please come to office hours. We'll have office hours. Mine is not determined yet. Actually, tomorrow I'll hold office hours from 2 to 4, 14 to 16. So feel free to come during that time if you have any questions related or unrelated to the course. This is just for tomorrow. Later weeks we will set some other office hours. And my TAs will also have office hours. They will be posted on the website, which I will also talk about later. Okay, and remember, I like giving these quotes, but how many of you know Louis Pasteur? Pasteurization? Yeah, he's a famous person. But basically, he said this. He says, chance favors a prepared mind, and I really believe that, actually. You need luck to be successful, that's true, but you increase the probability that you're lucky if you're prepared, if you actually do all of this stuff. And this is true in research a lot, actually. This is Louis Pasteur, by the way. This is true in research a lot. If you're a researcher, for example, if you are not prepared, you won't see the opportunities to make a big contribution. For example, if you don't have the background to actually see that a problem needs to be solved 5 years from now, then you won't get lucky to solve it, if you will. So chance definitely favors the prepared mind. And preparation takes time and education, for sure. Okay, so I think how you prepare and manage your time will be very important in the course, because there will be many lab and homework assignments. This is for your learning. It's not just because I want to dump assignments on you, but you will learn best if you have these assignments. So start early and work hard. That's my best suggestion. And homeworks, I think, are mainly for your benefit so that you can understand the material. Well, labs are also that way, but labs will take a little bit more time. So we'll probably have, this is not finalized yet, but we'll probably have 6 or 7 lab assignments of varying difficulty. And we'll start with some Verilog assignments early on, maybe 2 to 3. And we'll continue with some C-level assignments. Does that sound good to people? I know some people are good at Verilog, some people are less good at Verilog perhaps, but we'll have a mixture of both assignments. And that's as an architect, that's what you have actually. As a computer architect, if you design a system, you'll need to do both essentially. Okay, well, I think the key is you'll learn a lot of fascinating topics and understand how a computing platform works. And hopefully, I think, more broadly, hopefully this will change the way you look at and think about the designs around you. That's how I feel when I study architecture. For example, the way I go to a city and examine buildings, that changes my way. And I actually make it correspond with the topics that I actually do research in. I think that's the best way. Then you're really merging your research and your studies with the things that are around you. Okay, so hopefully you're not here for the grades, but we need to have a grading policy. And this is what it is. This is already on the course syllabus online. But projects will be important. There will be a midterm exam. There will be a final exam. And homeworks will be important also. So 50% of your grade will come from projects and homeworks, yes. Oh, no. This course is not even linked from my website. You must be clicking on something else. Yeah. But there is a course website. I will show that, and that will be linked from my website. But this is on the website, the course information website from ETH. There's a computer architecture website that you can find in the course schedule listing. Does that sound good? Yeah? Okay. So basically, I think projects and homeworks are really essential for your learning. I mean, this is true for the exams also, but if you do really good on the projects and homeworks, then we'll have some sample exams as well. Okay, more on this later. I don't want to talk too much about grading because hopefully everybody will get good grades in this course. Okay, so what will you learn? Well, computer architecture, of course. This is the broad definition of computer architecture. It's really the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy, consumption, cost, and other specific goals. It's a very broad definition, as you can see, right? So there could be other specific goals. But this is not the traditional definition. And traditional definition, this is from Jean Amdahl, Amdahl's law. How many of you know Amdahl's law? Okay, great. How many of you have read the paper that introduced Amdahl's law? Okay. Sounds like we have another reading assignment coming. The good thing is it's only 2-3 pages. So basically, Amdahl defined it as, and this was actually also known, but he put it in nice terms. The term architecture is used here to describe the attributes of a system as seen by the programmer, i.e. the conceptual structure and functional behavior as distinct from the organization of the data flow and controls, the logic design, and the physical implementation. So he basically makes a distinction between what the programmer sees and needs to deal with versus what the implementation, underlying implementation is that the programmer doesn't see. This is the traditional instruction set architecture definition, basically. Whatever the programmer needs to know to actually make use of the computer is really architecture, instruction set architecture. Whatever the programmer doesn't see, doesn't need to know, that's really microarchitecture or implementation. And that's the clean distinction. But in this course, we'll use architecture mostly, except when we try to distinguish between microarchitecture and architecture. This is Jean Amdahl. Apparently, he's holding one of his chips for an Amdahl 470 V6. Okay, so you've seen this before. And we've deconstructed it also because this may not be the best way of looking at the system, right? But it's still a good organized way of looking at a general purpose system. And computer architecture sits basically here, right? This is the ISA, this is Amdahl's distinction. But we will cover also microarchitecture and logic here. We may actually go into circuits today, in fact, a little bit. And we will cover some of the runtime system as well. And sometimes, actually, we will go to the higher levels, but we won't spend a whole lot of time over there. But of course, in your assignments, you'll need to deal with programming. And this is one of your required readings. We have not set the deadlines for the required readings yet because we're still setting up the website for the review, but you can start reading this one. This is a beautiful overview of computer architecture written by Yale Pat, whom I introduced you yesterday. That was written early at the beginning of the century, 2001. Now you can look at it, you can read it, it's beautifully written. A lot of the things still hold, but also evaluate it critically because some of the things that are described over there, some of the things that we see today are not really fully described over there, right? But you will see that when you read it, so I'd like you to evaluate it critically. Okay, so this is, we'll just deconstruct that picture. This is another view of the levels of transformation. By the way, levels of transformation was introduced by Yale. Not in this paper, but this paper formalized it. This is another view that I like to look at also because there's user that interacts with different components over here. And in the end, we want to design computing architectures for users and optimize the entire stack. So what will you learn? A little bit more. Basically, we will cover fundamental principles and trade-offs in designing the hardware-software interface and major components in a modern programmable microprocessor. That's what the assignments will be geared towards. We'll focus on the state-of-the-art and some recent research and trends and trade-offs and how to make them. You'll see that in today's lecture. You saw it in yesterday's lecture a little bit. And how to design, implement, and evaluate a functional modern processor. So this is what the assignments will be about. It's a combination of RTL implementation and higher level simulation. You'll start with some baseline RTL in the first assignment. And focus will be on functionality first, and then on how to do even better. So if you want to do more, of course, you're welcome to. But the key thing is to making it work. Key thing is making it work to begin with in the assignments. Of course, you're welcome to, for example, there will be an assignment on caches. You're welcome to optimize the cache and make it better and see the benefits of the mechanisms that you put in, either based on the papers that you read or whatever you would like to evaluate. That's always welcome, and you'll get credit, extra credit for that. But functionality is important too. And I think, in addition to this, how to think critically and broadly. I think that's really important. Whatever course you take, I think this is really a necessity in education. And how to work efficiently. Hopefully you'll learn that too, if you're not there yet. So. Two goals related to what I've just said. Basically, you'll be familiarized, assuming you're interested in computer system design, with both fundamental operation principles and design trade-offs of both processors, memory, and platform architectures. We'll cover interconnects also in today's systems. I already said this, I think. We'll talk about current and future issues, like we did yesterday, right? And we'll look backward, we'll look forward, we'll look up, and we'll look down. We'll look all ways, basically. And the second is the lab component. You'll hopefully have the necessary background and experience to design, implement, and evaluate a modern processor by performing hands-on RTL and C-level implementation. And again, strong emphasis on functionality, hands-on design, implementation, and efficiency. So these labs are actually quite nice because if you actually do good in this course, everybody will want to hire you. That's the way I like to think about it. A lot of past students in this course have taken two routes, for example. One route has been research, and people have actually published papers based on the stuff that they've done in this course, or later versions of this course. And other people have taken jobs in industry, and they're all over industry right now. Apple, Google, Intel, ... basically there, because of this experience. So hopefully people actually do startups too, but those remain to be seen if they're going to be successful. So this will enable you to do anything, hopefully, in the end. Okay, making things work, like we've discussed yesterday, right? Basically getting these things functional. The hardest lab will probably be the cache coherence lab. You guys know about cache coherence? Oh, okay. Maybe we're done. I don't need to teach you anything. No, it'll be fun. We'll talk about trade-offs. Which course did you cover cache coherence in? Here at ETH? Which course covered cache coherence? Do you remember? Oh, okay. Yeah. So did you go into the trade-offs of different protocols, for example? Okay, so... Okay. You have a comment, or? No? Okay. Yeah. Okay, yeah, that makes sense, I think, parallel programming. If you've taken a parallel programming course, then you will see that some concepts are similar. But here we will go a lot more into the trade-offs, assuming time permits, of course. Okay, so this is the course website. This answers your question. Let's go over there and see if it works. What do you think? Will it work? It works? That's good. It helps, I guess. So I should... Not advertising for any browser. I think none of them are that great. Okay, there you go. Yeah, this has some basic information, as you can see. Our contact. Oh, you cannot see. All right. So how do I make this over there without moving it? View, full screen. Say it again?
Did you exit your slideshow?
Did I exit my slideshow? That's a good question. Let's see. I did exit my slideshow. So maybe mirror the screens. What do you think? Yeah. I don't want to move it. Okay, arrangement. That looks slightly better. Now it's screwed up my screen over here. Okay. Okay, I'm going to move it. See, you cannot always get what you want in a fixed architecture. Let's see if I do this, it's going to fit. At least it did that. There you go. I don't know why it looks this way, but all right. So there's a sidebar which gives you to the lectures and schedule, so you'll see the slides posted from yesterday. And video is not available yet, but it will be. Maybe it's already available, but it's not uploaded. So we should have a link to the ETH website for the video also, because we'll put it on YouTube, but it's also on ETH. And you can see our contact information. And this is the email address you should send things to if you want answers quickly, because this goes to all of us, to me and the TAs. Let's see, what else do I want to show you over here? So you'll see that your homework, actually, I would like your homework 0, which is due on the 27th, but hopefully it'll be easy. You can email this to us at that. Actually, is that what we specified? Yeah, you should email it to us. Okay, so that's the website, basically. I'm sure you know how to navigate the website. And you have links to previous lectures for digital technique. So I will reference some of them, especially if you need some background for something. You can actually go there. And as time passes, we'll add the labs, exams, technical documents. And the readings from yesterday are posted, but they're going to be reorganized. Well, they're already reorganized. Well, one is quick. Oh. That's good. So basically, some of them are described in detail, some of them are suggested, so you can, if you're interested, you can just go and have fun. Does that sound good? Okay, perfect. Let's see. And there will be buzzwords also. I find this is useful for people to study later. Basically, these are some of the things that we've covered. It's not a comprehensive list, but this will quickly give you an idea of what we covered in a lecture. So that when it comes time, hopefully all the time is for studying, but when it comes time for reviewing, you can look at these buzzwords. Okay, I think that's all I want to say at the moment about the website, unless somebody has questions. Okay, I don't hear anything. That's good. Okay, so we will put more information over there. So this is a good place for you to look at reasonably frequently for announcements and due dates. Of course, class will have announcements in the class as well. Okay, so homework 0, I already showed you. Basically, this is information about yourself so that we get to know you. We can associate faces with names much more easily, and also what you're thinking about, like what you want in this course. This course is optional, so you don't need to take it for a requirement. So hopefully the answer to the question, why are you taking this course, is not to satisfy a requirement. But maybe it is. That's okay. It's okay. You can be frank. No problem. Okay. All future grading is predicated on this, basically. If if you don't submit this assignment, you'll get an undefined grade. If you do submit, then we'll do the regular grading. Okay, so heads up. So what's coming in the next few weeks? We'll have a few required review assignments due likely end of next week. We'll see. And homework 1 will be out early next week. And you already know what questions will come. The refresh question from yesterday is an example. Lab 1 will be out mid next week. And you'll probably have about 2 weeks to do each. And these will be announced, but also they'll be on the website. So some of them may be put up on the website earlier than the lecture happens. So if you check the website, you'll find them. Okay, any questions? So labs will be on your own, but we will have time slots, office hours, for example, and some of the lectures will be actually repurposed. So some of the lecture slots will actually become slots where you can ask questions on the labs. Okay? Okay, so any other questions? Okay, let's move on then to even more motivation on why study computer architecture a little bit. So we've already said this, right? This is the broad definition of computer architecture. And we will soon distinguish between architecture and microarchitecture a little bit more. And actually, we have done this in the digital circuits course if you've taken it last semester. But a big enabler of architecture has been Moore's law. And I'm sure you're all familiar with Moore's law. Who's not? Don't be shy again. Not knowing is not something to be shy about. Not learning is something to be shy about, I think. But this is Intel's, actually, picture that ends at 2005. Moore's law is essentially says that component counts double every other year. Double or something every other year. Or every 18 months. This is a law of... it's not a law of physics, clearly. This is maybe a law of economics or something like that. It's more of an observation than a law. But Moore observed in his 1965 paper, cramming more components onto integrated circuits. Moore is one of the founders of Intel, actually. He observed that he basically plotted over the years the number of components per integrated circuit. And he saw that basically it has this relationship. It's doubling every other year. And he said this is going to continue. And he also showed that actually it makes sense for it to double because as time passes, it becomes cheaper to integrate more components. And if you integrate less components, less devices, you're actually operating at a suboptimal point. If you integrate more devices, you're actually operating at a suboptimal point because your costs go higher either way. This is because, again, yield. Because of yield reasons, cost reasons, ... So he basically drew the curve that, as time goes by, the optimal point that minimizes manufacturing cost actually shifts. As a result, you have more components over time. That's essentially Moore's law. And the paper actually has arguments inside there, so you can look at it. And this is a more up-to-date version of it. This is 2011. This is even old. And you can see that we're already at 3 billion transistors per chip. That's actually higher today, right now. I don't know what it is. If you have up-to-date information, you can say. And this is going to continue for a while. Of course, people always say this is going to end at some point. There are physical limits. That's probably true. Yes. But we have not reached the physical limit yet. We are still making these transistors smaller and smaller. But as you see, as you saw yesterday with the Rowhammer problem, it is coming at a cost in some domains, right? In memory, for example, as you make things smaller, you become less reliable. That's true for logic also. You become less reliable when you make the transistors smaller also. Okay, but this has been an enabler for computer architecture for a long time, right? And this is an only 3-page long paper. This is one of the quotes. With unit cost falling as the number of components per circuit rises, by 1975, economics may dictate squeezing as many as 65,000 components on a single silicon chip. So we're way beyond 65,000 components right now, right? 40 years later. Maybe 5 billion components. Components meaning transistors today. Another quote, which is actually forward-looking by him, will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? And this has already become a problem, actually, in modern chips. The modern chips are not limited by the number of transistors that you place, but number of transistors you can keep active at the same time, number of transistors you can switch. Because every switch leads to energy consumption. If you're switching too much, then you may actually be causing a lot of heat and leading to thermal degradation, right? That's why we can actually put more transistors than we can switch on the chips today. And how do you design the system given that sort of a constraint? So what people do is today put accelerators, for example. The accelerators are not always on. They occupy area, but they're turned on when they're really needed. So that's one benefit that Moore's law has enabled, on-chip accelerators, right? We have all these transistors. We can put these accelerators that are not always on, but that are enabled when they're needed. The good thing is they're enabled only some of the time, which means that not all of the circuits are switching. As a result, you don't have this thermal problem, hopefully. But also, you can accelerate applications much more efficiently because you've accelerated them, like a video encoding accelerator, right? It's not always on, hopefully, unless you're always doing video encoding or decoding. And this thing has probably 50 accelerators or so in it, some of which are not disclosed. Okay, so it's always good to think about this. You put more components, but it comes at a cost. Even though even though your cost overall may be reducing, you may not keep them active. Right? So energy consumption has become a problem today. And whenever we talk in this course, we'll talk about the energy implications. So always think about the energy implications, even though I may not explicitly talk about that. Because here, everything is about not performance. It's really about the performance that you get for energy that you expend. Area is also a concern, but it's really the energy. That's the limiter of innovation here. Okay, what do we use these transistors for? Oh, sorry. Your readings for this week should give you an idea. So this is the required reading that I mentioned, so you can start doing this. We haven't assigned a deadline yet, but that's okay. And there will be required readings as part of homework 1, and these are basically the 3 things that we've discussed yesterday. I'm not going to require all of them. Maybe I'm going to let you pick 2 or 3 or 1. Not 0. You should do at least 1. Okay, so what has this enabled? The ability to put more components on chip has enabled us to build better systems, right? We have much faster, much cheaper, much smaller, and maybe, hopefully, much more reliable computers today, right? And we've done this by exploiting advanced changes in the underlying technology and circuits. And that's come as a result of the computer architectures that we've built on top of that. And we've enabled new applications. Again, 20 years ago, we didn't have lifelike 3D visualization. Maybe we'll have virtual reality sometime soon. Self-driving cars, personalized genomics, personalized medicine. All of these are things that require a lot of computational power. And new applications are enabled because of this computational power that we can put on the chips. We can enable better solutions to problems, even though some problems may be okay to solve. We can enable better solutions, right? Software innovation, or more features in the software. Software innovation has been built on trends and changes in computer architecture. And historically, for a long time, every year performance has improved. The hardware performance has improved by more than 50%. And that has enabled a lot of innovation. Now the question is, this has become harder to do, of course. That's one of the reasons why people have moved to multi-core, because single-core performance has become harder to improve. If this tapers off, how do you actually improve performance, right? That's why people are looking at accelerators today, right? Because it's still, again, I'll pick on deep neural networks from yesterday. If you have this tensor processing unit, that enables significant performance improvement, and that enables software innovation. Maybe you don't get the 50% performance improvement by general purpose changes to the cores, but with specialized accelerators that you can afford because you have a lot of transistors on chip. And I think the last, maybe one of the most important reasons actually that enables all of these is to understand why computers work the way they do. That's one of the big reasons to study computer architecture. Because if you understand this, you can enable all of this in the best way, I think. Okay, today I think is especially important and exciting time to study computer architecture, because this was not the case 20 years ago, maybe. I mean, I started my studies in architecture actually more than 20 years ago, so, well, about 20 years ago. So it was always exciting to me. But today is even more exciting because today we're in a large paradigm shift. People are still moving to multi-core, experimenting with a lot of different things. It's not clear what are the best potential system designs. That's why you see all these accelerators like the TPU or many accelerators that are integrated over here. And multi-core, even that might not be the best design, right? Because that's not good for software in the end. And there are many difficult problems that exist today that are both motivating the shift, this paradigm shift, and caused by the shift. For example, power and energy. That has been a huge constraint in the last 2 decades. If you look before, it's not that big of a constraint. But today, we're really limited by power and energy in all kinds of systems. some more than others. And this is also driving heterogeneity, for example. Heterogeneity means instead of having components that are the same, you have components that are different. Accelerator is an example, right? You have a general purpose core and an accelerator. A general purpose core and an FPGA, a CPU and a GPU together, right? Complexity of the design has become a lot, again, recently, because a single core performance has become difficult to improve, as we've discussed yesterday. And that has opened up multi-core and heterogeneity again. I have a misspelling over here. I wish this automatically corrected these misspellings without asking me. Wouldn't that be nice? Okay, and that complexity, again, we're designing ever more complex systems today. That's not going to change again. Of course, simpler is better, but by nature of the problems that we have, things are becoming more complex. And as we've seen yesterday, there are big difficulties in technology scaling. In DRAM technology, we're seeing errors. In other technology, we're seeing errors. So this opens up potential for new technologies, and we will talk about that. Memory is a huge problem. That's why we're starting this advanced course with memory. And memory has always been a problem, but as we've seen yesterday, moving data from memory into the processor chip actually consumes much, much more power, 3 orders of magnitude more power than doing a complicated double precision floating point addition, right? This means that maybe we need to rethink the system, and this is already happening in the field. Maybe we should do more processing close to the data, inside the memory, without moving the data. So we'll talk about that. And you're at a nice position right now, because these ideas, you will see that they've been proposed in the 1960s, 70s, but they never had impact in real life, because things were good at that time. But today, things are not that good. We already have a huge data bottleneck, so people are actually considering doing processing in memory. And if you understand that, you can actually build the systems of the future, where you can actually do minimal data movement and processing close to the data. Reliability is a problem which is related to the technology scaling. Again, we'll cover that more and more. You've seen that yesterday a little bit. Programmability is a problem. And always you make choices in hardware. You make the design less complex, you run into programmability issues. Or maybe more complex, you add too many accelerators, that also runs into programmability issues, right? So there's an interesting thing in programmability. So if you make the system not so programmable, you can easily have an irrelevant architecture. And I'll give you examples of that. One example, cache coherence we were talking about, right? Do you actually have cache coherence in a multi-core system or not have cache coherence? Let the programmer deal with shared data. Well, in a general purpose system, if you don't have cache coherence, your programmability suffers significantly, and most programmers will not be able to program that system easily. And this happened, for example, IBM in early 2000s, I think, designed this first innovative processor. It's called the Cell Broadband Engine. It's a heterogeneous multi-core processor. It had one processor, that's the control processor, and 8 different processors that are, they called it synergistic processing units, and this one the primary processing unit. And their decision was to not have cache coherence. They said basically programmer deals with all of the shared data accesses and caching. So they had scratchpad memories. And it turned out this work, which was really interesting and ahead of its time, but it really didn't have much impact. It was used in PlayStation, but after that, it was not used for anything after that, as far as I know. So programmability is always important, and we will see that more. And there's a huge hunger for data and new data-intensive applications today. That's not true before. Right? And I think the more important thing is perhaps there's no clear, definitive answers to these problems. So having all your understanding is really important, understanding of the technology, architecture, all of the different trade-offs, and having the ability to think critically will enable you to design much better solutions. Okay, just a little bit more. These problems affect all parts of the computing stack if you do not change the way we design systems. Basically, as I've shown you as an example, the Rowhammer problem affects almost all parts of the computing stack, right? Programmability affects all parts of the computing stack. Maybe it enables, it basically stops someone from using whatever you design over here, right? And things are changing. There are many new demands from the top, from the problems, many new issues at the bottom. And there are fast-changing demands and personalities of users also. Again, we're designing for the users, but the users are changing as well, right? They're more impatient, if you will, as time goes by. They want more real-time response, right? If things don't work, they just drop it and go to the next vendor, if you will. So again, so the landscape is very different from 10 to 20 years ago, both at the software and humanity trends, and both down at the technology level and their issues, and forward and backwards, and the resulting requirements and constraints. Which means that every component and its interfaces, as well as entire system designs, are being re-examined today. So that's why we have this heterogeneity, that's why we have heterogeneity in memory, that's why we have these accelerators, that's why we're thinking about new technologies. So you're at a good point. Which means that you can also revolutionize the way computers are built if you understand both the hardware and the software. And you can change each accordingly and know how to make trade-offs. Because I don't really, I'm not really exaggerating when I say that every component's interfaces are being examined today. I'll give you one other example, which is the memory interface. Memory interface has been constant for decades and decades and decades. Memory has been a dumb device, but people are examining to change that interface today because they're seeing this as a big bottleneck. How do you change that interface? Well, I think that could be something you can do. You can invent new paradigms for computation and communication and storage, and people will consider it today. Whereas 20 years ago, 30 years ago, they would probably kick you out of the room. I'm just kidding. But 20, 30 years ago, if you look back a little bit, things were good in the sense that, for example, Intel and AMD, they were able to design single-core processors that are more pipelined, much more higher performance every year. Every year, they would get 60% or so performance improvement out of their designs by changing the microarchitecture, also getting benefits from the circuits technology. Today, that's not the case, basically. Today, people are very hungry for new ideas. Okay, I'll recommend one book. How many of you read this book? Thomas Kuhn, The Structure of Scientific Revolutions. No? You're not required to read this? I know nobody reads books anymore in the world, but maybe I'm just exaggerating. So this is a philosophy of science book, actually. I used to give out this book as a prize for people who did well in my assignments. Maybe we'll do that here also. If you're not going to read it, let me know so that I don't give it to you. But this is a book that analyzed how a lot of scientific revolutions over the history of time, and that analyzed how revolutions happen. So before a paradigm gets set, there's no clear consensus in the field. People actually explore many different directions. And at some point, there's the normal science period. There's a dominant theory that's used to explain and improve things. I call it business as usual. Exceptions are considered anomalies. So for example, 20 or 30 years ago, pipeline, superscalar, out-of-order processors are really the dominant theory. In this case, give me a little bit of grain of salt. It's not a theory, of course, but it's really the main design paradigm of the time. And everybody was doing that. And that was the dominant thing because people were able to get much better performance. And exceptions, like things like GPUs, were anomalies, actually. But over time, that theory didn't satisfy things. As a result, you go into revolutionary science. Basically, you need to re-examine the underlying assumptions. We're not improving performance anymore with this superscalar, out-of-order designs. What's the problem? Well, the problem is it's not scalable. We need to make them more efficient. And maybe there are other paradigms, like more parallel processing, processing in memory, that can actually enable much better systems. So we're at a point in computer architecture and computing platforms in general, maybe computing systems actually, where there's no clear consensus in the field again at the moment. We don't have a dominant way of designing computing platforms. Okay, and that's Thomas Kuhn. So I would recommend this book. I didn't give you, he has a lot of other examples in how actually science evolves and revolutions happen, but I think this has been criticized a lot, actually. A lot of people have written books to criticize this view of the world. But I think this is, at least this high-level view explains how things evolve at some level. Okay, and that's the older edition of the book. This looks like the newer one. Oh, okay, there's a Kindle version also, too, yeah. Since people don't read books, you can have a Kindle. Is this Kindle? Well, good, it's not visible what that is. Okay, but first I think we'll need to understand the fundamentals to be able to revolutionize things, right? You can change the world only if you understand it well enough, right? Because you can always say, oh, I'm going to change the world, and you can design a system that's going to be used by no one. Right? Or no one but you, maybe. especially the past and present dominant paradigms and their advantages and shortcomings, in other words, trade-offs. And what remains fundamental across generations. I think this is really important also. And what techniques you can use and develop to solve problems. So that's why I will cover some fundamental concepts. But maybe we should take a break for 5 minutes. Okay, 5 minutes and then we'll continue. All right, our 5 minutes are up. Let's get started. So we have covered a lot of fundamental concepts in digital circuits, but we will cover some more here. I'll start with what is a computer. A computer has 3 key components, right? Computation, communication, and storage, memory. And storage and memory have been the same actually in the past, but now we have a distinction between them, which may change with emerging technologies. But basically, this is the high-level view that I like thinking about when I think of a computer, right? And we will cover all 3 components, but we will start focusing more on memory, because digital circuits and your background probably focused a lot on the processing side. And we will talk about von Neumann model. Hopefully everybody's familiar with the von Neumann model. Yes, who's not? Again, don't be shy. Okay, good. So you can tell me what are the 2 key properties of the von Neumann model then, since everybody's familiar. If you remember. I'll take one. Yes?
I think one is that memory program and storage
Uh-huh.
the same memory.
Yeah. So it's a store.
Flow between the memory and the
Yeah.
CPU.
Okay. Yeah, I think you're getting at the stored program, notion of stored program. Program is stored in memory. Yes, it's a stored program computer. Yes, that's one characteristic. What about the other one? Yeah, that's true, but there's one more that's really fundamental. Yes, sequential instruction processing, basically. Stored program and sequential instruction processing. I mean, there's a lot more that's explained in the von Neumann model, but these are the 2 hallmarks of it. Stored program means instructions are stored in a linear memory array, and memory is unified between instructions and data. And the interpretation of a value inside memory depends on the control signals. And if you've taken digital circuits, which most of you have, you've seen that, right? Whenever you access memory, whenever you're fetching an instruction, that location that you access, the data that you get is treated as an instruction, right? If you access the same location, when you're fetching data from a load, that location will be treated as data, right? So there's no separation between instructions and data really, except for the control signals that you use to interpret it. And the second, and this is important, certainly, but the real fundamental part of von Neumann processing that is, well, I already said this, the answer to that question, right? The real fundamental part of von Neumann model has been sequential instruction processing that has affected the programmers quite a bit, basically. The abstraction is that one instruction is processed at a time, fetched, executed, and completed. There's no, the next instruction doesn't start before this instruction finishes. It's sequential. Sequential means somebody needs to orchestrate that sequence, and that orchestrator is the program counter or the instruction pointer. Right? Instruction pointer is a nicer name, I think, because it's a pointer to the address of the instruction that's going to be fetched, executed next. That identifies the current instruction, and the program counter is advanced sequentially. It's incremented, basically. It's incremented with the size of the instruction so that you go to the next instruction. Except for control transfer instructions, of course. But control transfer instructions jump to some other part of the memory array, but they're still executed sequentially. Right? Everything is sequential. So this is nice because the programmer can clearly reason about it. Right? They know that this instruction is going to be executed before this, and this is before that, ... So debugging becomes extremely simple. And if you've taken digital circuits with me, we talked about the notion of precise exceptions, and that enables a lot of other things also, but we're not going to talk about that today. So this is actually the paper that is introduced, actually, the von Neumann model. So this is not a required reading. This is a recommended reading. If you're interested, you can look at this beautiful paper that actually covers a lot of concepts early on, since it's written in 1946. Right? And again, if you're interested, the von Neumann model also is beautifully explained in this book chapter that we've covered again in digital circuits by Yale Pat and Sanjay Patel. So stored program and sequential instruction processing. And this is the view of the computer, basically. You have this processing unit, you have this memory, and you have this control unit. And the control unit determines how the data over here is interpreted, and whether it's interpreted as an instruction or data, and you have this input-output. Okay. Since we're critically thinking, my first question would be, is this the only way that a computer can operate? Is the von Neumann model the only way? It's yes? No. So there's a clear no. That's good. So a qualified answer is no, but has been the dominant way. So this is, for example, most ISAs today obey the von Neumann model, right? So it's been the dominant paradigm for computing. But even this may change going forward. And for n decades, it's been the dominant paradigm, right? So let's take a look at a different model. Have you guys studied the Dataflow model in the past? No? So you haven't taken digital circuits with me, so this will be new. That's good. We covered it in digital circuits. But von Neumann model, an instruction is fetched and executed in control flow order, right? Dataflow model is I wouldn't say opposite, but completely different. An instruction is fetched and executed in the data flow order, meaning when its data operands are ready, the instruction gets fetched and executed. There's no program counter. So there's no, in von Neumann model, you have an instruction pointer that says, we're at this instruction, we're going to execute this instruction next. Yeah, you are sequential, your control flow is sequential unless there's an explicit control flow instruction. In the data flow model, an instruction gets fetched and executed when its operands, when its data is ready. There is no instruction pointer. Basically, there's no need for the instruction pointer. I mean, you need to know the address of the instruction, but there's no need to point to the next instruction that you're executing, because instructions are executing when their data values are ready. So instruction ordering is really specified by the readiness of the data, or the data flow dependence, in other words. Each instruction specifies who or which other instruction should receive the result. So basically, each instruction has a pointer to the instruction that it's going to supply data to. This is not necessarily a next sequential instruction, right? This may be somewhere else in memory completely. And an instruction fires whenever all of its operands are received. Fire meaning it's really fetched and executed. Right? So this way, you don't need any program counter or instruction pointer. Right? So potentially, many instructions can execute at the same time, right? Because you're not really constrained to saying, oh, I'm going to execute this instruction at this point of time. Many instructions can be ready to fire at the same time, right? Because, again, you're not controlling it. Okay, which means that this is inherently more parallel. Yes?
How do you branch?
Yeah.
If there's no jumps in the instruction?
Yeah, that's a great question. I'll show you. Yeah. Have you heard about predicated execution? Okay, we'll see the data flow model, but you can also you don't also need to have branches even in the von Neumann model, because you can convert the branch to a data flow dependence. Right? You can say, for example, instead of having a branch that says you should go to this instruction next, you should go to this if this condition is true, do this instruction. If this condition is not true, do the other instruction. You can say, I'll evaluate the condition and set a bit, and then go to the next instruction. If that bit is true, execute the instruction. And if that bit is not true, then the instruction doesn't do anything. Turns into no op. So you can actually eliminate the branches even in the von Neumann model. And Dataflow does something similar, actually. But you will see more when we cover an example. So we'll actually talk about control flow dependence handling. We'll talk about predicate execution a little bit more. So, okay, consider a von Neumann program. Let's actually deconstruct this program. This is purely sequential. There's no branches intentionally here to make life a little bit easier. So I have two questions over here. What is the significance of the program order over here? And what is the significance of the storage locations? So the program order clearly gives you a nice ordering of instructions that you can reason about. But beyond that, it doesn't provide much, right? In the end, what you're really trying to do is, well, you can figure out what that is. I'll build the data flow graph soon. But significance of the storage locations, if you look over here, you add a plus b, store it into v. You add b times, you multiply b by 2, you store it into w, and then you basically do v minus w to get x, v plus w to get y. And then you multiply x and y to get z. Assume that your output is only z and you don't care about whatever else is produced. So the storage location, this w, is there to just hold an intermediate result, right? It's really there, a plus b, this v is really for communication between these two instructions. You store this result into v, and this x, this instruction over here consumes that result. So that's the purpose of the storage location is really communication. A value you produce needs to go somewhere, so you store it somewhere, and then the other instruction loads it from somewhere. So you can eliminate all of that storage if you are, well, you can potentially eliminate all of that storage if you actually have a data flow execution model. So this is the data flow version of that program. And usually in data flow, you think graphically. That's the easiest way to think about. But again, you need to, of course, translate this into an ISA, and we'll see that in a little bit. But basically, this is exactly the data flow version. And you see that the storage location, V, that's A plus B, V is over here, right? It's really represented by this arc over here. And node is an instruction. Arcs are basically values that are communicated between the instructions. And you don't need to store anything over here. You just need to communicate the values. There's no need for a register, if you will. Does that make sense? And you can see that this is inherently parallel. You can clearly see that these two instructions can go in parallel. Probably these two instructions can go in parallel, actually. And this instruction can go by itself. But maybe if the program is bigger, there may be other parallelism over here, right? And there's no ordering between these instructions because there is no control flow. These instructions can both fire when its values are ready. Okay. So which model is more natural to you as a programmer? Which one would you program with? This graphical thing or this thing? Anybody? The sequential one? Yes? Everybody says sequential? Who says data flow? Oh, there must be at least one data flow person here. Yeah, this is, so it's not clear which one is really more natural inherently, but a lot of people pick this one because that's the paradigm, right? That's the dominant paradigm in my opinion. But this may be more natural if you actually were born that way. I don't know. If you were educated that way. We'll see. But this is, clearly, this enables more parallelism. If you want to get parallelism out of this, you need to figure out the dependencies, right? But here, the instructions fire whenever their data values are ready. Okay, so how does it work? We're not going to cover a whole lot into the data flow. We may have a lecture later on. But if you're really impatient, I'm going to point you to some lecture videos. But I'll cover a little bit. So in a data flow machine, a program consists of data flow nodes. Looks like this. A data flow node fires, which means that it's fetched and executed when all of its inputs are ready. This is also called when all inputs have tokens. So a data flow node looks like this, and in the ISA, it can be represented like this. Basically, this is potentially an instruction encoding, right? You have the operand, you have the opcode, you have the first argument, whether it's ready or not. You have the second argument, whether it's ready or not. If it's ready, you get the value here. If it's ready, you get the value here. And when both bits are set to 1, this node fires. And it gets the arguments or values at that point. And this is the destination of the result, which means that where should this go? Which instruction should it enable? So if this is connected to, for example, here, the destination of the result indicates the instruction at, this has to have a memory location, the instruction at memory location, let's say 120, and the result goes to the right input value. Right. So there's an argument on the right and the left, so you need to specify both. And this also sends the result somewhere else, right? So you could actually have multiple destinations, depending on the ISA that you design. Or you need to have a copy node over here that copies the result to multiple different locations. Make sense? So basically, you can encode this data, this graphical program as a set of instructions that look like this, that are connected together. That's the ISA level. So, okay, let me take a step back. This is converting the data flow into ISA level, but you can also implement this data flow completely in hardware, right? You can have an adder, you can have a multiplier, you can have a, basically you can have a subtractor, you can have another adder, you can put all of this into hardware directly. And when the input values arrive, hardware just combinationally produces the output value. That's what you can do in an FPGA, for example, right? So that's also data flow. Except that's not ISA level data flow. That's basically baking the data flow graph into your hardware. This is more ISA level data flow. You basically have a data flow ISA. Okay, and people have actually looked at these data flow ISAs in the past. They've never been really successful for reasons that we may discuss. But data flow, okay, you asked about the branches. You can have branch nodes that look like this. Basically, it's a conditional node. Remember, I said tokens. So let's take a look at this. So this instruction, when it gets a token here and a token here, when both of its tokens arrive, it can fire, and it generates another token after it executes. Tokens are basically, the value is really available over here, right? You can visualize it that way. So for the branch instruction, you need two tokens. Basically, this is the data token, this is the control token. And the data token, when both of those tokens arrive, you can make a choice. If the control token says take the false output, the data token goes to the false output in this case. If the control token says you should take the true output, then the data token goes to the true output. That's how you can actually branch or direct the data to the right instruction. That's essentially what branching is. Relational, that's another example. That's how you generate the conditions. In this case, it's a relational that's greater than. If the left token, if the data value of the left token is greater than the data value of the right token, you generate a true output. Otherwise, you generate a false output. So you can connect these nodes, and as a result, you can get a data flow graph. And this is a more complicated one, as you can see. So it can actually be arbitrarily complicated in your data flow nodes. Right? That's, again, that's a characteristic of your ISA. If you're designing an ISA, you can have a very complicated instruction that looks like this. Do you know about barrier synchronization? So barrier synchronization is a method of synchronizing threads, let's say, or threads of execution, such that when all of the threads reach a point, they can continue only after that. Right? All of the threads need to reach a point to be able to continue after that. They synchronize at a barrier. They need to reach that barrier. This is an example. Basically, if all of the tokens arrive, only after that you send the tokens out here. This is a simple barrier node. There may be many other variants of this. Make sense? Okay. So now that it makes sense, you can solve this puzzle that I'm going to give you. Maybe. Any questions on this? We can go on and on, of course. So this is one other data flow program. This is an example, full data flow program that does something. Maybe it's not the most efficient way of doing the thing that it does. In fact, it's not the most efficient thing, but it's one way of doing it in a data flow program. So I'll ask you what it does, so you can start thinking about it. Basically, here we have 1. It doesn't look like a 1, but it's 1. So this is the initial input. And here we have n. That's the initial input. N can be some value. It's when the program runs, it's input, basically. It could be 8, it could be 10, it could be 1 billion. And initially, there's a token over here. There's a token over here. And what the output is coming out of here. So the question is, what does this program do? Now, I'll need to give you some more thing over here. There's this weird thing that happens, right? If you look over here, this arc over here joins this arc that's incoming. That means that when there is no token over here, the token should come from here. So it's like a loop, basically. That's just the semantics of the way it's been drawn. There's another one over here. The output that's coming from here joins here. So if there's no token over here, the token should be taken from there. Right? Oh, the EC is decrement. Sorry. Yeah, you need to know the ISA to be able to figure out what this is. This is greater than 0. Copy, as I said, copies basically whenever there's a token over here, it duplicates the token. It copies it into both outputs. And I think that's all you need. And this is a multiplication. And that's greater than 0, I said that, I think. So what does this do? Oh, you guys are quick. Shall we wait or? Okay, yeah. Okay, what is your thought? Yeah.
I thought it was I for n.
I think he's right. Okay. I think he's right too, actually. So he was quick. It does compute n factorial. Does everybody see that? So basically, let me go through it very quickly. So initially you have n. So the operation is very simple. This node fires whenever it has a token. And I told you that it has a token to begin with. So it fires, it generates 2 tokens. So n goes here, and this n goes here. And you can execute it in different ways, right? So you can execute in parallel over here also. Okay, let me say. So this 1 over here is ready, but this Boolean is not ready yet because there's no token coming out of here. So this cannot fire. So the first node that needs to fire is this one. It fires, it generates 2 tokens, n. This fires because it has only 1 input, n is greater than 0. So it generates a true output. And this fires again when it generates a true output because it's a copy node. So true goes here, true goes here. Now at the time true goes here, we know that this will fire because this has already a token over here. We know that this will fire because this is n over here, right? So you get n over here, so n goes here. And here you get 1, true, 1 goes this way, right? And n goes this way, I think. This has become n. So you get n times 1 over here. And you get n over here, n minus 1 over here. Now you get n minus 1 over here, and n over here. So if you followed what was happening, we're really multiplying the 2 values that come over here. So we multiplied n with 1. Now we have n minus 1. So we have n times n minus 1 next. And then we'll have n times n minus 1, and then n minus 2 over here. So we'll multiply those. And then we'll have n times n minus 1 times n minus 2 over here, and then n minus 3 over here, and then we'll multiply those. So you're basically getting the n factorial, assuming n is non-negative. Right? Yeah. If n is negative, then I don't know what this outputs. It probably doesn't end, yes? Could you say it again? Is the Boolean value supposed to be what? Oh, okay. So, it's always true if n is positive. So if n becomes, at some point, you keep decrementing n becomes 0, and 0 is not greater than 0, right? At that point, you get false over here. False get copies here. And the value that you have over here dies. This is the dying node. I didn't say that, sorry. But that's the ground. You basically lose the token. And you get false over here. And the value you have over here, which is supposed to be n factorial, gets output. Okay? So it's not always true. Make sense? So this is a data flow program, basically. You executed your first data flow program, probably. Okay, ISA is a different issue. How do you implement this in a real machine is a different issue, which we're not going to cover for now. But, and actually people have implemented these machines in the 1970s, 1980s, ... And it turns out it's very difficult to design these machines at the ISA level. So in the end, what happened, well, we'll talk about that ISA level. In the end, what happened is people took the von Neumann code and internally executed this way. So a lot of the machines, if you've taken digital circuits, you would have learned the out-of-order execution machinery. Basically, a lot of the machines that we have today take the sequential code, turn it into a data flow graph that looks like this, and execute the instructions in the order of data flow, not the sequential order. And at the end, they reorder the instructions such that the programmer sees the sequential order. That's how you get the high performance. So basically, at the ISA level, you're still von Neumann, but internally, you're data flow. That's called the restricted data flow. And all high-performance out-of-order engines operate this way today. This engine here operates this way. All of Intel processors are that way. Okay, so but let's look at the ISA level. Do we need an instruction pointer in the ISA? That's basically the trade-off we're making over here. If the answer is yes, you get control-driven sequential execution, one Neumann model. An instruction is executed when the IP or instruction pointer points to it. I use IP and PC interchangeably. I like IP, instruction pointer, which is Intel's terminology because it makes more sense. But program counter is also fine. IP automatically changes sequentially, except for control flow. If the answer is no, then you have data-driven parallel execution. An instruction is executed when all of its operand values are available. That's data flow. And there are many trade-offs over here, many high-level ones. Basically, how do you program this other one? Most of you said you can program the sequential one more easily, right? That's probably true, actually. In fact, there is one issue over here with programming the data flow machines, debugging, right? For example, in sequential machine, if you have a bug in your program, you know where the bug is, hopefully, if you have precise exceptions, meaning an instruction, if an exception happens, you know that the previous instructions have finished and none of the later instructions have started. So you have a clean point. You can set a breakpoint in your program, and you're sure that because this machine satisfies the von Neumann model of execution, you're at that clean point when your breakpoint stops. Whereas in a data flow machine, everything is executed in parallel, right? It's really the order of execution is dependent on the availability of data. And availability of data may be dependent on many things that are going on in the system, right? Things may get delayed because somebody else is accessing memory at some point. So at this point in time, you get a bug in your program. When you re-execute, you may not see that bug at all. Or maybe see that bug somewhere else. So debugging is very hard because you don't have a precise state. You don't have a point in your program where you can say, these instructions are done, but none of the other ones are done. Because you don't control that. There is no control. So that's the really hard part of programming a data flow machine at the ISA level. Ease of compilation is another issue. How do you compile to these? Maybe that's less of an issue. Performance. Which one's higher performance? Well, inherently, one would think that data flow is higher performance because you expose all of that parallelism at the ISA level, and that's probably true. In fact, one of the problems with these data flow machines that people have built in the 1980s was the control of parallelism. They said there's too much parallelism we cannot control. We don't have enough hardware to store all of these instructions that are pending. That's actually amazing, right? All of these programs have so much parallelism that it overwhelmed the hardware. Because if you think about how to implement this data flow machine, some of the instructions have some operands are ready, some of the instructions, and some operands are ready, some operands are not ready. So you need to store them somewhere. You need to figure out which instructions are available to execute at any point in time. And that buffer can become really large if you have a lot of parallelism in your program. So data flow is inherently much more parallel, and control flow is less parallel. But as I said, people today implement out-of-order execution internally do data flow to extract some parallelism out of this, but it's still restricted data flow. Hardware complexity, again, another thing. If this is the case, the hardware complexity is actually higher because of what I said earlier. This is lower because you can restrict it, perhaps. Right? But then converting the von Neumann model to an internal data flow representation may add more hardware complexity also, right? That's essentially what today's machines do. They convert that, and people have tried to reduce that complexity as much as possible by incorporating a little bit of data flow principles into the ISA of von Neumann machines also. But we're not going to talk about that. That's more advanced later on. So, okay, as I said, a similar trade-off, control versus data-driven execution, can be made at the microarchitecture level. So you can actually think of these trade-offs as independent. You can have a control flow, von Neumann machine, control flow machine at the ISA level versus data flow machine, and you can have a sequential machine, I should say sequential versus data flow at the ISA level, and sequential versus data flow at the microarchitecture level. And you can combine all options. You can have 4 different options, right? Some of them may not make sense. So basically, ISA specifies how the programmer sees instructions to be executed, right? And microarchitecture is how the underlying implementation actually executes the instructions. You don't have to obey the sequential order as long as you report the sequential order to the programmer. As long as the programmer doesn't see what you do, you can do anything in the hardware, right? So a programmer sees a sequential control flow execution order in the von Neumann model versus programmer sees a data flow execution order. And in the microarchitecture, again, as long as you obey the semantics specified by the ISA, you can do anything. Just don't make the mess visible to the programmer. Right? When making the instruction results visible to the software, you should be careful. So programmers should really see the order specified by the ISA. So that's exactly why today a lot of high-performance microarchitectures are out-of-order execution data flow principles, but ISAs are von Neumann sequential ISAs. Okay, so if you want to, we'll get back to the von Neumann model now, but if you want to learn more about data flow, this is one of the first papers about it. This is from Jack Dennis. He was the first proponent of data flow, and it talks about what I just showed you, some of the data flow graphs. And this is one of the data flow computers, and this may be harder to understand, but there were a lot of data flow computers that were built in 1980s. And this talks about that data flow computer, the Manchester prototype data flow computer. But if you're really impatient, you should really watch this lecture that talks about some of these. And these will be linked from your readings site. So, and this is not required by any means. This is just for people who really want to understand or learn more. You'll have enough to learn about in the required part of the course. So if you look at today, most of the instruction sets use the von Neumann model. They're sequential, whatever you can think of. But underneath, the execution model of almost all implementations are different. So you can have pipelined instruction. So modern processors, high-performance processors are out of order, but we used to have only pipeline processors, right? Intel 80-486. Do you guys remember this, or you're too young for that? I think most people here are too young for that. My first computer, well, other than the Commodore 64, my first Intel-based computer was on 386, not even a 486. So Intel 486 is a pipeline instruction computer. Multiple instructions at a time. Intel Pentium introduced that in order, pipelined. Out-of-order execution was introduced by Pentium Pro, basically internally data flow, externally sequential. And also separate instruction and data caches. They also have separate instruction and data caches internally. Right? This may be, even this is breaking the von Neumann model strictly, right? You're really storing things at different places. So what happens underneath that is not consistent with the von Neumann model is not exposed to the software, basically. You reorder things at the end. And that's the difference between ISA and microarchitecture. Okay, we've already discussed this, basically. This is the traditional ISA definition of computer architecture. So let's go back to the ISA versus microarchitecture a little bit. So ISA, in the end, is an agreed-upon interface between software and hardware. This is what the programmer, software, compiler is also written by a programmer, assumes and the hardware promises. It's a contract. In other words, if you're ever faced with the question, should this be part of the ISA or is this part of the ISA, you should always take the litmus test, which is this what the software or some software writer should know to write and debug system or user programs or write a compiler? Right? You can always answer whether something is part of the ISA by answering that question. So microarchitecture, on the other hand, is a specific implementation of an ISA. It's not visible to the software. So for the x86 ISA, you can have 1 million different implementations that are all different from each other. Because they're not exposed to the programmer, you can do anything underneath. And a microprocessor is basically ISA, microarchitecture, and circuits, all of them at the same time. And sometimes people use architecture as ISA plus microarchitecture. This is the definition that we use, not the traditional definition. Okay. So what is part of ISA versus microarchitecture? I like thinking about this as an interface, right? So for example, cars. A lot of cars have different implementations underneath, but you always have a gas pedal, right? Gas pedal is the interface to accelerate for the car. And that doesn't change across cars, at least across most cars, right? Maybe there are some cars where the gas pedal is, I don't know, somewhere else. But for most cars, that interface is there, and that interface doesn't change. Whereas internals of how that acceleration is implemented, that changes from car to car, right? And implementation can be various as long as it satisfies the specification. And you can actually apply this to many, many things. For example, add instruction. Add instruction is part of the ISA because the programmer needs to know that there's an add instruction as format to be able to program. But the implementation of the adder, the programmer is not exposed to it, at least in most reasonable ISAs, right? Internally, for example, you can actually add two 32-bit registers that needs to be exposed to the programmer The programmer needs to know that to be able to do the addition. But internally, you can implement it as a bit serial adder. You guys know about bit serial adders? Basically, every cycle you add a bit, 1 bit at a time. So if you're adding 32 bits values, it takes 32 cycles. It's very efficient in terms of circuit because it's small, right? But it takes time. So the trade-off you're making over there is it's small circuit, probably efficient in terms of power, but then it takes 32 cycles to do an add. This may be okay if you're doing billions of adds and you can parallelize them, right? But if you're doing only one add, you need to wait 32 cycles. Or rippled carry adder, which makes it more parallel. Carry lookup adder, it makes it even more parallel so that your critical path is lower. They're all part of the microarchitecture, right? That implementation doesn't need to get exposed to the programmer. For example, x86 ISA has many implementations that make many different choices for adders, ... right? And we can study some of those when time comes. And as a result of this, microarchitecture usually changes faster than ISA. ISA doesn't change because the programmer needs to change their code when the ISA changes significantly, right? In fact, one of the most important things in the ISA, if you want to keep the existing software running on future hardware, you need to be backward compatible. You need to basically keep the features that you had in your ISA in the past. Because people have written code assuming those features, right? Assuming those instructions. When you change the ISA completely, that code doesn't work anymore, right? So people don't change the ISA, they add to the ISA. As a result, ISAs become bulky over time. So when x86 started in the 1970s, it was not this bulky. Today, it's one of the most ugliest ISAs because it accumulated all of these instructions over time. And they cannot take out instructions because if they take out instructions, they lose some software that cannot run in future hardware anymore. So that becomes a little bit ugly. But microarchitecture can change faster internally because it's not exposed to the software, right? You don't need to change any software when you change the microarchitecture. Okay, so what is ISA? I think this is, you can take a look at it. It's actually anything that's exposed to the programmer in this manual. That's another definition of the ISA, because this is really the contract, right? And this is an older version probably of Intel's thing. It includes instructions, opcodes, addressing modes, data types, instruction types, formats, registers, condition codes, things about memory, how is virtual memory organized, address space, addressability, alignment, interrupt and exception handling. I'm just giving you this. We're not going to cover all of these. Some of these are covered in earlier courses anyway. Access control, how is that handled? I/O, how is it handled? Task management. Power and thermal management, more and more. These are actually parts of the ISA today because the operating system writer needs to know what can you change in the microarchitecture, right? How do you change the DVFS, the dynamic voltage and frequency states? Multi-threading support. All of these need to be known to the software developer. Again, some software developer, maybe not all software developers utilize all of these, but some software developer needs to utilize this to write an operating system, for example. Okay, microarchitecture, on the other hand, is the implementation of the ISA under specific design constraints and goals. Pipelining, for example. Even that breaks actually the von Neumann model, if you think about it, right? You're really starting an instruction before you finish another instruction. You pipeline the execution. And that's done underneath. It improves your parallelism. If you expose the pipeline registers to the programmer, now pipelining is part of your ISA. But most systems don't do that. Right? In order versus out of order instruction execution, we talked about that. Memory access scheduling policy. How do you reorder the requests, building upon yesterday's memory performance attacks? That's also microarchitecture, right? The programmer doesn't need to deal with that. But again, you can expose anything to the programmer. In fact, John Koch, another Turing Award winner by IBM, he is the father of RISC, what later became to be called RISC, reduced instruction set computers. He basically advocated a system where control signals are exposed to the programmer. You have this very low code, you expose all of the control signals to the compiler, let's say. Actually, he said compiler, not the random programmer. But the compiler, if it actually sees all of the control signals of the program, it can generate a much more efficient program. And he actually, this mentality, this what you would potentially call crazy thinking, generated a lot of research into the compilers at IBM, and actually that's the reason he got the Turing Award, because he had this crazy idea that you should expose these hardware at the very low level to the programmer, to the compiler, and make compilers that optimize programs by taking advantage of these very low-level control signals. At that point, the control signal is part of the ISA, right? That sounds terrible. In the end, that's not what's happening today, but that gives you an example, right? Any of these can be part of the ISA, but most of them are not today. Speculative execution branch prediction, for example. You predict a branch, that's done internally, right? That branch prediction doesn't get exposed to the ISA, at least in most cases. We'll talk about branch prediction later on, but there are hints that are provided in branch instructions that are part of the ISA today. The programmer can specify this branch is likely to be taken. And that is part of the ISA. And that helps. If the programmer is correct, then the hardware can easily say, oh, this is likely to be taken. The programmer told me that, so let me jump to the target. Superscalar processing, meaning multiple instructions at the same time. That's not exposed to the ISA today in most machines, but if you've taken my digital circuits, you've seen the concept of very long instruction word processors. There, the idea was the compiler packs multiple instructions that are independent together, saying, oh, these instructions can be executed in parallel. The hardware, you don't need to do any checks because I know that they can be executed in parallel, and you should just fetch all of them together and execute them in parallel. That's the VLIW, a very long instruction word machine. Now, you can do multiple instructions parallel in a VLIW machine, and that's part of your ISA. Your ISA is inherently parallel, right? It's sequential across those instructions, but each very long instruction word consists of multiple operations at the same time. And you go to the next instruction, and then the next instruction, and the next instruction, but each instruction can do, let's say, 28 operations, right? 28 actually was the number of operations that you could do in the multi-flow machine by Bob Caldwell. So Bob Caldwell actually designed a lot of the VLIW machines at that time. And then later he went to Intel and designed the Pentium Pro, which is the first out-of-order execution one Neumann machine. So he figured out, I think, the VLIW didn't work as well. Although VLIW has been successful, but you can, we may cover that later on. But you should really, if you're interested in this, you should look at the digital circuits lecture. Okay, clock gating. So one of the ways of saving energy is gating the clock. Right? Gating the clock means you basically make the clock zero so that your clock signal doesn't get supplied to a circuit block. For example, if you're not going to use your floating point unit, you can gate the clock to it such that you don't consume any clock power in it. Is that part of the microarchitecture or the ISA? Well, that depends on who does it, right? If it's done completely in hardware without being exposed to the programmer, then it's part of the microarchitecture. Today, most of it is part of the microarchitecture, actually. But you could potentially think of exposing it to the programmer, right? If the compiler, for example, can analyze the code and say, oh, we're not using the floating point unit, maybe it should give a hint to the hardware saying, oh, turn off the floating point unit, right? Something like that. There's also power gating, which is even more aggressive. You not only turn off the clock, but you turn off the power to that unit. So you don't even consume static power, no leakage power. So today, all of these are done, in most processors, they're done in hardware purely. So they're part of the microarchitecture, but you could imagine them being exposed to the software as well. So caching, we'll talk about caching, hopefully, if I stop this part. But caching, again, is that part of the microarchitecture or is it part of the ISA? Again, we may think about how many levels of cache, what is the size of the cache, what is the associativity of the cache, what is the replacement policy of the cache. Do you guys know about all of this? Who knows about caching everything? Okay, that's great. Who doesn't know about caching? Who didn't have a course in caching? Okay. We'll cover caches, so that's important. We'll start with caches today and talk about some trade-offs. But is this part of the ISA? So if the software doesn't need to know about caching, it's not exposed, then it's part of the microarchitecture, right? But if, for example, the ISA specifies, I don't know, maybe not the associativity, but ISA has instructions that can move data between the caches, hints, then that cache is exposed to the software, right? Then it's part of the ISA. At least part of the cache is part of the ISA. Prefetching. Now we're getting to more interesting territory. Well, again, this could be part of the microarchitecture if it's done purely by the microarchitecture without exposure to the software. But if you have instructions that enable the software programmer to say, oh, load this data, even though I won't need it right now, load it into the cache or load it somewhere into the prefetch buffer. Preload it. Then that's part of the ISA, right? Voltage and frequency scaling. And that's another way of saving energy. When you don't need that much frequency, that high frequency in your processor, you can reduce that frequency. Is that part of the ISA or microarchitecture? Again, the same thing. If it's done purely in hardware, then this is part of the microarchitecture. But in most systems today, actually, this is exposed to the ISA. At least some part of it is exposed, maybe not all of it. Because there is a range for voltage and frequency, and some part of that can get exposed to the operating system such that the operating system can do this voltage and frequency scaling dynamically. But you may not need to expose all of that if you do it internally. Right? Error correction, that's another thing. Whenever you correct an error, do you expose that to the ISA? Right? Maybe it's a good idea. Do you expose that to the software, right? So at some point, this becomes very nebulous, right? What should you do? And this is all part of the trade-off, actually. I've just given you a bunch of different trade-offs that you can do. And your complexity changes significantly depending on which one you choose. And we haven't even talked about, like, should you really do prefetching in software or hardware? We'll get to that, actually. Since we're starting with memory, we'll talk about prefetching in a few lectures' time, I think. OK, let's look at some examples. I'll ask you, is this a property of ISA versus microarchitecture? What do you guys think? Add instructions opcode. ISA? Microarchitecture? No one says microarchitecture, and you're right. Yes, this is clear, right? This is the ISA itself, almost. Number of general purpose registers. ISA? Okay. Microarchitecture? Have no idea? Okay. So this caused some controversy. So general purpose registers, this is actually part of the ISA in most systems because the compiler needs to know about it. Right? The compiler actually, the register IDs, they need to know about it. Now internally there may be other registers that are not exposed, but they're not usually called general purpose registers. Number of ports to the register file. How many reads can you do from the register file? ISA? Microarchitecture? Okay. Yeah, that's right. This is microarchitecture. At least in most systems, again. Because people don't deal with the ports in the register file. It's usually the microarchitecture's job. But, again, you can imagine a system where you specify which port of the register file that this instruction is going to use. The compiler can do that, right? In John Cox's system, yes, you would definitely do that. Some VLIW machines actually expose this. Number of cycles to execute the multiply instruction. ISA? Okay. Microarchitecture? Okay. Looks like you're overruled. Well, yeah.
I think it could be a part of the
That's right. I mean, all of these actually could be.
I mean, like, if the compiler knows what's the latency and what's the throughput of the instruction,
Yeah.
document, we can see that in documentation, and actually produce a better code. We can rearrange it so they can be better. I mean, it could be part of the ISA.
That's right. That's right. So that's true, but it can change across generations. Right. Yeah. Target microarchitecture. Yeah. So this is where things get a little bit nebulous, actually, because this is a useful thing to have for the compiler for the reason that you suggested. Basically, the compiler can reorder instructions. It's usually not considered part of the ISA. It's really part of the microarchitecture because it depends on the implementation. But people actually expose it. People say, for example, for this Intel processor, the multiply takes 56 cycles. I don't know. That's a long multiply, of course, 6 cycles. And people optimize the code. But then they say this can change in future. So this is just the specific implementation. So in a sense, in that way of specifying, it's really not part of the ISA. They basically say, for this microarchitecture, it's going to be 6 cycles. For this other microarchitecture, it's going to be 7 cycles. So this enables microarchitecture-specific optimizations. So, and then it gets nebulous because I told you earlier that whatever the compiler needs to know to generate code is part of the ISA. Now we have a contradiction. But in this case, it's whatever, it's really, they basically specify it very carefully. For this microarchitecture, it takes this cycles, this many cycles. So I would consider this part of the microarchitectures because of that reason. Whether or not the machine employs pipeline instruction execution, ISA, Okay, microarchitecture. Okay, I would go with the microarchitecture again, because this is usually not exposed to the program. But again, you can consider exposing it, right? You can consider saying to the programmer, oh, we have a pipeline this deep, and the compiler can optimize the code that way. Compiler actually, it's good for the compiler to have that information if it's going to, for example, decide between using the branch prediction hardware or eliminating the branch using predicated execution that we discussed earlier. Right? It's a good idea for it to know how long the pipeline is. What is the misprediction penalty?
When would it be better to use the elimination branch?
Yeah.
When the pipeline is deep, then
So it really depends, I think. If it's dependent on multiple factors. Again, we'll cover that in the control dependence handling lecture. But it's dependent on how good of a predictor you have. What is the wasted instructions if you actually predicated the branch? Because if you predicate the branch, you'll fetch some instructions, and some of them will be no-ops later on. And also how deep your pipeline is. And how long it will take to resolve the branch also. Because that's dependent not only on the depth of your pipeline, but it's also the data dependencies that you have. So it's a very complicated decision, actually. And most compilers are not good at doing that. Okay, so this hopefully gives you some idea. But so the last one I would consider, again, microarchitecture. Because even if you expose it by saying, oh, this microarchitecture has this kind of pipeline. Okay. Okay, so let's talk about design point as well before we take another break. We're going really slowly today. That's unfortunate, but that's okay. That's good. We are having discussion. Basically, design point is a set of design considerations and their importance. This leads to trade-offs in both ISA and microarchitecture. Basically, what are you designing this system, platform, processor, or memory for, right? And there are many considerations, as we've seen yesterday. Cost, performance, maximum power consumption, energy consumption, which are different, availability, reliability, maybe correctness, time to market, and you can keep adding to this, right? And this design point is really determined by the application space. What are you designing for? And not only application space, but also the intended users and the market, right? What is your goal, if you will? And it's really important that you know your design point well to optimize your system, right? And, for example, I'll pick on the TPU again. If Google was designing the transfer processing unit for external customers, maybe they would have made very different choices, right? But they were designing that tensor processing unit internally for their own use. They had a very specific design point in their own data centers for very specific workloads that they knew exactly what were. Now, if that changes, if that design point changes, maybe the thing that they designed will be suboptimal, right? So design points also change. Okay, the application space, there are many applications. I'm not going to cover that. This is actually from your reading, which is actually nice. It gives you some applications, but clearly, I have not seen a paper that talks about all kinds of applications yet, because this is really depend on the imagination of people. So the soul of computer architecture is really about the trade-offs. And you can make this trade-offs in many levels. I've just given you ISA level trade-offs. And we've also talked about microarchitecture level trade-offs. There are also system and task level trade-offs, how to divide the labor between hardware and the software, right? And computer architecture is really the science and art of making the appropriate trade-offs to meet a design point. And there's no single best way, if you will. Why art? Hopefully it's obvious by now. Because we don't really fully know the future, right? Even the present, we may not fully know, right? Who's going to use this thing? You have a design point, sure. You have a target set of applications, sure. You know those maybe, but there's also stuff that you don't know that people are going to use this for, especially when Intel, for example, designs processors. They have no idea what it's really going to be used for out in the field. Anybody can take it and use it for their purpose, right? So it's also art. Basically, we've discussed this over here. And things are changing also. It's not also, if things were constant, maybe you could predict it, right? But if things are changing, if the problems are changing, if what people are executing is changing, and if the technology is changing, issues are changing over here, and the users are changing, then this becomes really an art, right? Unless you can model all of these very precisely and figure out what you need to do in your clock gating mechanism to satisfy all of those changing requirements, this really becomes an art. It's not the pure art, because there is also science behind it, because you know some things, but it's really the combination of it. Okay, So this is really, adapting to the future is really part of the task of a good computer architect. So you have many, many options. We call this the bag of tricks, if you will, and we'll see a lot of bag of tricks over here in this course. So keen insight and good design is important, actually, to exercise those options. Good use of fundamentals and principles. So some principles, for example, heterogeneity and reconfigurability are good things that enable you to adapt to changing demands. If your design is extremely strict, then if something happens in the future, it will not be able to adapt to it, right? But if you are heterogeneous and maybe reconfigurable, you can adapt to it much better, right? You can patch things better. And there are levels of reconfigurability and heterogeneity that already existed in the past that may exist more going into the future. And good use of underlying technology. That's also important. Okay, so we covered a lot of this in digital circuits and computer architecture. After I finish these slides, we'll take a break. But I'll give you an overview of what we're going to cover later in this course. So if you actually took digital circuits with me, this is what we've covered. I know many of you didn't. Sorry. You can come back and take it next semester. I'm just kidding. But basically, we covered logic design, Verilog, FPGAs, ISA, single-cycle microarchitectures, multi-cycle microprogram microarchitectures, pipelining, a lot of issues in pipelining, some of which we're going to cover more about, out-of-order execution and other execution paradigms, and very, very briefly, memory and caches. So this course, we're going to pick up on this part, actually, because this is actually one of the most important parts of a system today, which we cannot cover in a single course, everything, unfortunately. That's why we have these two courses as a sequence right now. But we covered a bunch of concurrent execution paradigms. So this part of the execution paradigms, we covered pipelining, out-of-order execution, data flow very briefly at the ISA level, similar to what I've covered right now, superscalar execution, VLIW, which also I talked about briefly, SIMD, single instruction, multiple data processing, vector and array processors, GPUs, and decoupled access execute, which is, anyway, you can read the work, and systolic arrays. Systolic array is interesting because Google's tensor processing unit is actually a systolic array. If you're interested in it, maybe we'll cover it later on. But if you want to brush up, if you want to learn more about any of those, feel free to look at the lecture videos. I'm not going to assume that you know all of this stuff. You may not have seen it. If you've taken it from me, then you should know all of that stuff, but you haven't taken it from me, so that's okay. But you can always look at the lecture videos online. And we may later in the course come back to some of these different paradigms. We're definitely going to come back to control flow handling, for example. And you can also find all of the slides and the assignments online. But I will point you to some lectures that could be useful, particularly for this course, if you want to brush up. Pipelining is certainly one. Dependence handling and pipelining. These are actually 3 lectures on pipelining, really. And out-of-order execution could also be useful, although probably less so than pipelining. So if you want to brush up, all of the materials available online. You can go and watch the lectures, read the slides. Well, but in this course, we will definitely have more emphasis on the memory system, multiprocessing and multithreading, which all systems are today, and parallel processing paradigms. And we will likely dig deeper on some digital circuits concepts, like ISA, which we have talked about briefly, and branch handling. Branch handling is important because it actually presents itself a lot in all of these over here. Well, maybe not the memory system as much, but certainly multiprocessing and multithreading. So this is kind of the tentative agenda of the course going forward. We'll talk about memory hierarchy. I was hoping that we were actually talking about the memory hierarchy right now. Caches, virtualization a little bit, virtual memory, main memory, a lot about main memory, memory latency tolerance and prefetching, the state-of-the-art that happens in existing systems, and we'll talk about non-volatile memory and emerging technologies. And then we'll do a significant amount of multiprocessing, cache coherence and consistency, interconnection networks, multi-core issues, and multi-threading. Actually, multi-core issues will be intermingled over here also, because you cannot separate today's memory hierarchies from multiple different cores, as we've seen yesterday, right? Does this sound good? So this is the plan of the course, basically, going forward. Okay. Okay, this is a good place to stop for 5 minutes again. Maybe let's give it 20-second more margin. We have not even started memory hierarchy. so we're already behind, but that's good. Let's see how aggressive this agenda will be. You think it's all doable? What do you guys think? Does it sound exciting? You'll in the end learn all of what a modern system has, basically. And some future what it will have, hopefully. Okay, let's get started. So these are some optional readings. None of this is required. Actually, there's no book that is assigned for this course. The material that I cover is really not covered in any book. Bits and pieces are in papers, books, ... But I don't think there is any book that covers what I would like to cover. That's why there is no book that's assigned. But for memory hierarchy and caches, there's an ample amount of material out there. And I would recommend, if you're interested in brushing up or supplementing what I've described, you can look at this chapter from Patterson and Hennessy. This will be posted. PNH means Patterson and Hennessy. There's also a Hamacher book, the first 7 chapters in memory and cache. And an early cache paper by Maurice Wilkes. It's not the first cache paper, but I'm going to talk about it. It's the most intuitive and insightful first cache paper. Okay, so memory. We'll talk about memory. And programmers' view of memory is this, basically. You just load and store to it, and memory magically gives you data and writes the data, right? But we're going to break that internal thing over here. So abstraction, programmer sees virtual memory, at least in most systems. Again, this is not the case in all systems, but we virtualize memory for good reason. By virtual memory, programmer can assume the memory is infinite, right? That's not exactly true, but that's the abstraction, right? Sometimes you can run out of virtual memory also. Hopefully you're not doing things to run out of virtual memory. But the reality is physical memory size is much smaller than what the programmer assumes, and somebody gives the illusion. The system software and the hardware cooperatively maps virtual memory addresses to physical memory. What kind of a sentence is this? Sounds bad. Okay, that's better, right? The system maps virtual memory addresses to a physical memory, which means that the system automatically manages the physical memory space transparently to the programmer, giving the illusion that there is a large amount of physical memory, whereas the physical memory may be small. So you've covered virtual memory before, right? Most of you. Who doesn't know about virtual memory? Everybody knows? Yeah? Should I assume everybody knows about it? Okay, we'll spend less time on virtual memory in the future then. Okay, so the upside, again, even this is a design choice, right? The upside of virtual memory is programmer doesn't need to know the physical size of memory, nor does he or she need to manage it, right? A small physical memory can appear as a huge one to the programmer, and life is easier for the programmer, right? In fact, this is one of the things, if you actually go to an interview, I would love to ask this sort of question, for example, to a candidate. If there is one thing that has really made life easier for the programmer that the computer architectures have provided, what would it be? My answer would be virtual memory. It's really there for the programmer. Of course, the downside is now you have more complex system software as well as hardware architecture, right? Hardware architecture needs to be more complex because you need to accelerate this virtual to physical translation. System software needs to be more complex because it needs to manage all of that movement between the physical and virtual memory. Virtual memory meaning the disk space. So this is a classic example of the programmer microarchitecture or microarchitect trade-off. Microarchitect's life is harder, programmer's life is easier. And this has been extremely successful. So we're going to talk about more physical memory system. You need a larger level of storage to manage a small amount of physical memory automatically. Physical memory has a backing store. This is called a disk today. It could be an SSD, it could be in something else, right? But we will first start with the physical memory system. For now, we're going to ignore the virtual to physical indirection. That's an abstraction that's on top of this, right? We will get back to it a little bit when the needs of virtual memory start complicating the design of the physical memory. And there will be some cases that this will happen, especially in the context of caches. But let's ignore that for now. So let's look at a computing system again. This is another view of the computing system. You have an instruction supplied. You supply the instructions to the pipeline. You execute the instructions, and instructions need some data, so you need to supply the data also. So memory is really both sides, right, over here. So a pipeline we've covered a lot in digital circuits. We may come back to it again, as I said. But ideally, it's always good to think about the ideal. What do you want in a system? Idealism helps you to build better systems. So ideally, you want no pipeline stalls. And we've covered some of that in digital circuits. You want perfect data flow, no dependencies, but also you want to know the dependencies that exist very quickly. You want zero cycle communication. You want enough functional units to sustain the parallelism that you have. And zero latency compute. Right? That's ideal. That's what you want in the end. And people have tried to design the pipelines to approximate that ideal over time. Of course, it's not possible. You get into trade-offs, right? If you want zero latency compute, something else you need to give. So we're going to talk more about the memory system. So both instruction and data supply are very similar in what we want, except for this part in instruction supply. We want zero latency access, infinite capacity, zero cost, or enough capacity, right? At zero cost. And perfect control flow in the case of instruction supply, right? That's a specific problem with instruction supply. Data supply, we want zero latency access, infinite capacity, infinite bandwidth, and zero cost. Bandwidth is less of a problem in the instruction supply because we normally don't fetch a whole lot of instructions at the same time. But this could also become a problem depending on how many instructions you're fetching, right? Okay, so we'll talk about the memory hierarchy. This is the picture I've shown you yesterday. And again, let's talk about the same requirements. We want zero access time, infinite capacity, zero cost, infinite bandwidth to support multiple access in parallel. And in high-performance processors, we have multiple access in parallel today. So the problem is the ideal memory's requirements oppose each other. Let's take a look at the size versus latency trade-off. Bigger is slower, faster is more expensive. And higher bandwidth is also more expensive. So if you want bigger, it takes longer to determine the location. If you want faster, your technology needs to be different. SRAM, DRAM versus disk versus tape. As you go down that way, you become slower and cheaper. Higher bandwidth is more expensive. You need more banks, more ports, higher frequency, or faster technology. We'll cover some of these in the later lectures. We'll talk about banks, for example, ports, ... Whenever you want higher bandwidth, it's more expensive. You need to pay for it. And usually, this is actually easier than the faster. Faster, you need to pay for more. But we'll talk about that too. So let's talk about some of the technologies, because technology actually affects a lot in memory. We've seen DRAM yesterday. Any kind of memory technology needs to have two things. One is the storage device, and the other is the access device. In DRAM, the storage device is this, which is the capacitor. And the capacitor charge state indicates the stored value. Whether the capacitor charged or discharged indicates storage of 1 or 0. Now, charge doesn't mean 1. Charge doesn't mean 0. It really depends on how you encode it. Right? You can encode the charged capacitor to be 0. You can encode a charged capacitor to be 1. Right? It's an encoding issue. Charge doesn't inherently mean 1 or 0. And you have one capacitor, basically. That's the storage device. But in order to be able to access it, you need to have the access device, which is all of this infrastructure that's around that capacitor. The access transistor, the word line or row enable line, and the bit line over here. Okay? So how you access it, you basically enable the access transistor. Capacitor shares the charge with the bit line and perturbs the bit line. And initially, bit line needs to be pre-charged to a value that the capacitor can perturb. If this is discharged, it'll perturb it down. And the sense amplifier that's sitting over here will sense that perturbation and say, oh, this is a 0. If it's charged, it's perturb it up. And the sense amplifier will sense that perturbation and it's going to increase the charge and think that it's a 1. Of course, 1 and 0 may be different, right? Again. So capacitor leaks charge through this RC path, resistance conductance path, and DRAM cell loses charge over time, and we've discussed this before, right? DRAM cell needs to be refreshed. But this is very dense technology, as you can see. It's one capacitor, one transistor. That's it for the cell. SRAM, on the other hand, is static. It's not dynamic. It's not based on capacitor. But it's more expensive because it requires 2 cross-coupled inverters to trap the value in it, to store a single bit. This feedback path enables the stored value to persist, not in the sense of non-volatile persistence, but as long as you're powered on, the cell actually keeps its value. It doesn't lose that charge. There are 4 transistors for storage. Each of these is 2 transistors. And then you need 2 transistors for access, a bit line and bit line bar, because that makes the sensing simpler by having 2 transistors, and you do differential sensing SRAM. Okay, so clearly this is more expensive, right, because you have 6 transistors. But this is faster, actually, because you have a lot of charge in this. Capacitor charge sharing is a much harder process to sense compared to this differential sensing through the bit lines here. So memory bank organization is kind of independent of the technology. All of the memories kind of look like this, right? And we've seen this before, right? You supply the address, you have some most significant bits that basically encode the row, and you have some least significant bits that encode the column. And you first, to be able to read from this memory, you first decode the row address and drive the word lines. It's actually just one word line over here. And selected bits over here drive the bit line. So the entire row gets driven. You read the entire row. And then you amplify the row data. There's usually a sense amplifier over here, which is not shown over here, so that you can actually read it out. And you need to decode the column address and select a subset of the row. In this case, it may be this one, for example, if the least significant bits specify that, and then send it to output. And then when you're done with the access, you need to pre-charge the bit line such that you can actually sense the data values of the cells that you're going to access the next. Pre-charging basically prepares the array for the next access by setting the bit line values to a particular reference value. And all of the charge-based memories work this way. So SRAM, let's take a look at it. Basically, in SRAM, each of these locations consists of this, basically. And this is what you do. I'm not going to go over this in detail again. Basically, you read the entire row together again. You do differential sensing because you have bit line and bit line bar. Of course, there are many kinds of SRAM also, but this is kind of a dominant sensing mechanism for SRAM. And you pre-charge all bit lines later. So access latency is really dominated by driving the row select signal through the word line, and also the third one, bit lines being driven vertically. So it's really rows driven, and the bit lines are driven. So they're dominated, access latency is dominated by 2 and 3. Cycling time, which is a property of memory, is basically when can you start the next access? You have one access and you have another access. When can you start the next access? That's called the row cycling time or cycling time. It's dominated by 2, 3, and 5, basically. You drive the, again, word line driving, bit line driving, and pre-charging. And this is true for DRAM also, actually. So if you look at the step 2 is word line driving. It's really proportional to the number of bits you have, the number of bit lines you have, 2 to the m, because you need to go through the entire column size. And the step 3 and 5 is proportional to the number of rows you have. It's basically, you're really dominated by the interconnect latency. That's what I'm saying over here. The interconnect dominates your latency. Okay, so DRAM is very similar, except you'll notice the difference in the figure over here. So if you look at SRAM over here, because SRAM is fast, you can supply the, well, there are 2 reasons, actually. SRAM is fast, and also it's on chip, usually. So you can supply the address bits for both the row and the column at the same time. Whereas DRAM, it's almost always is in a separate chip. That's why we have latches over here. Basically, you supply the row address first, you latch it, you access the row, and then you supply the column address next. Why? Well, basically, if your chip boundary is over here, now you're saving some bits. You're not supplying n plus m bits at a time. You're supplying maximum of n, comma, m bits. This basically saves the pins into the DRAM chip, reduces your cost. That's why it's been traditionally this way. There's no reason you cannot supply n plus m together, other than the fact that it'll increase your pin count. Okay, I think we've discussed this. Basically, bits stored as charge on node, and bit cell loses charge. When it's read, bit cell loses charge over time. So read sequences are very similar, and the amplification is a little bit different. Basically, sense amplifier of DRAM is kind of different. There's a flip-flopping sense amp that looks like SRAM actually over here, and it amplifies and regenerates the bit line, and the data is muxed out after that. Regenerating the bit line meaning you regenerate the data, because once you read the data in the bits, you really destroy it. That data flows into the bit line as a perturbation, and that perturbation needs to be sensed and amplified and written back into the row. And you need to pre-charge all the bit lines at the end. So the reads are destructive here. Reads in SRAM are not destructive, because the charge is flowing always in that cross-coupled inverter. So reads are destructive, and you also have charge loss over time. And you need to refresh it as a result. So reads are destructive, but once you activate things, once you amplify, you restore the data So automatically, the circuitry ensures that you don't lose data when you read. When you read a row, you automatically refresh it, because you've actually done sense amplification, and sense amplifiers have written the data back. But if you have not read a row for a long time, you need to refresh it, basically. So this is another, you can start thinking about this now. We refresh every row every 64 milliseconds, but if we're reading the rows all the time, we don't need to really refresh those rows, right? That's true. It's not done today. How to do it efficiently is a problem, actually, because now you need to keep track of the rows that you read a lot, and you don't need to refresh, and that turns out to be complicated. Okay, so DRAM versus SRAM in one slide. DRAM is slower access because capacitor is slow, actually. Higher density, lower cost. It requires, unfortunately, refresh. And manufacturing requires putting the capacitor and logic together. And these are very different manufacturing processes. In fact, when people want to scale to very, very low dimensions, what they do is they actually etch this capacitor in a three-dimensional way. So even though I draw it like this, it's really a three-dimensional capacitor, and the excess transistor is on top of it. And that three-dimensional capacitor, the aspect ratio is almost 1 to 90 today. So that's a huge, you really drill into the silicon. It's crazy. And things are not as regular also. People try to place these things in almost like a hexagonal manner, such that they optimize the area that you get. So things are not exactly next to each other. So that also changes the capacitive coupling effects significantly. So people do a lot of tricks to make sure that the density is very high. And that's what's making it harder and harder to manufacture DRAM. SRAM is faster access, lower density, because it says 6 transistors. People have proposed other types of SRAM, but 6-transistor SRAM has been very common. It has higher cost as a result. There's no need for refresh, which is nice. And the manufacturing of it is compatible with logic process. There's no capacitor, so this can easily be used in a microprocessor that already has logic, right? So the problem is bigger is slower, and faster is more expensive. This is some data I'm not going to go over, but as you can see, these are the latencies and capacities that are roughly constant in terms of cost, I guess, something like that. I didn't do this calculation recently, so maybe it's not true. But it's true that you can access SRAM with smaller nanoseconds, whereas hard disks are much slower, right, because of the reading process. As a result, but then capacity can be higher over here. And these are some of the costs that you can see. Okay, and these are sample values from earlier. And other technologies have their place as well, and we'll talk about that later on. Flash memory, phase change memory, magnetic memory, some resistive or memoristive memories. They're not mature yet, some of them. Of course, flash memory is very mature. But they have their place as well, which are not here. So we have a variety of technologies that we can use as an architect. So why do we have a memory hierarchy? Because we want both fast and large. But we cannot achieve both with a single level of memory. The idea of the memory hierarchy is to have multiple levels of storage. They become progressively bigger and slower as the levels are farther from the processor. And hopefully you will ensure that, or somebody ensures that most of the data the processor needs is kept in the faster levels. Right? So this is a pictorial view of it, basically. What you need is here, what you don't need is here, but when you need it, you anticipate it and you bring it over there. So if you have good locality of reference, memory appears as fast as this and as big as this. Right? So that's the idea of a memory hierarchy. But it becomes more complex, of course, because you have trade-offs associated with it. To give that illusion that it's as fast as this, maybe you need to add more levels. Right? Okay, so basically the fundamental trade-off is this. Fast memory is small, large memory is slow. Memory hierarchy enables you to get the best of both worlds, hopefully, or approximate the best of both worlds. And if you look at this hierarchy, register file is also part of the memory hierarchy, except it's very special, right? It's directly exposed to the compiler. And there are many trade-offs over here: latency, cost, size, bandwidth, and they change from going from left to right. So locality is what enables memory hierarchy in the end. If you didn't have locality, if everything was completely random access, it's not clear if this would make sense. In fact, it probably doesn't make sense, right? How do you actually take advantage of this fast memory if you don't have any locality? And locality essentially means that one's recent past is a very good predictor of his or her near future. So if you just did something, it's very likely that you will do the same thing again soon. That's temporal locality. So since you're here today, there's a good chance you will be here again and again regularly. And that's already been confirmed with one data point from yesterday. And spatial locality, if you did something, it's very likely you will do something similar or related in space, right? So every time I find you in this room, this is the first time I find you in this room, but you're probably sitting close to the same people. You have some spatial locality, right? For whatever reason. Don't break that spatial locality. That makes it harder for me to find you. And that's exactly what it is, right? The computers actually, if you have spatial locality, computers are faster also. I'm faster if you keep that spatial locality for me. Okay, so a typical program has a lot of locality in memory references because typical programs are composed of loops. A program tends to reference the same memory location many times within a small window of time. That's temporal locality. Spatial locality, a program tends to reference a cluster of memory locations that are close to each other in the address space at a time. Why? Because you're going sequentially in the instruction stream. That's one example, right? That gives you spatial locality. Or you're going sequentially traversing an array, right? For I equals 0 to n, add these two arrays. That's spatial locality for you, right? A lot of programs are that way. So caching was developed to exploit temporal locality, to store recently accessed data in automatically managed fast memory called cache. The anticipation is that the data will be accessed again soon, and temporal locality hopefully provides that, right? And this is what Maurice Wilkes had in mind when he wrote this 3-page paper, right? Basically, he says the use is discussed of a fast core memory of, say, 32,000 words as a slave to a slower core memory of, say, 1 million words in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. That's basically it. That's temporal locality. But also spatial locality can be exploited with caching. You can store addresses adjacent to the recently accessed addresses in automatically managed fast memory. And the way we do it is we logically divide memory into equal sized blocks. And these blocks are larger than a word that you're accessing with a single instruction. And fetch to the cache the access block in its entirety. You basically fetch 64 bytes as opposed to 64 bits, hoping that the processor will access the 64 bytes around that 64 bit that it's referenced. That's the anticipation. And again, as I said, this anticipation is true. And the first time it was exploited was in IBM 36085, which actually had one of the first processors that had the cache. It had a 16 kilobyte cache with 64 byte blocks. It's amazing that we still have 64 byte blocks. But yeah, it has 64 byte blocks. And this is a beautiful paper that talks about the caching design in System 360. It also introduced the idea of sectored cache. How many of you know about sectored caches? Oh, good. If we have time, you're going to learn something today. Okay, so I like this bookshelf analogy. I know nobody reads books, but how many of you read books? Like real physical books? Oh, okay, sorry. How many of you don't read books? You hate them. That's fine too. Okay, basically book in your hand. You're exploiting temporal and spatial locality over there. Boxes in storage. There are some books that you really don't want to read. They live in boxes in storage. Right. And recently used books tend to stay on desk. Computer architecture books, hopefully. Books for classes you're currently taking. Until the desk gets full, the cache gets full, right? Or unmanageable. You kick them out of the cache, right? And adjacent books in the shelf are needed around the same time if you organize your books well, right? So that's the principle of spatial locality. But that requires organization of data. And that's exactly true for caches also. If you want spatial locality, you'd better organize your data well. Okay, so caching in a pipeline design. This is actually interesting because caching interacts very tightly with the pipeline. But this happens in the level 1 cache. The cache needs to be tightly integrated into the pipeline because ideally you want one cycle access to the data so that the pipeline can move, right, quickly. Dependent operations do not stall, basically. But with a high-frequency pipeline, and if you want one cycle access, you cannot make the cache large, right? That's the problem. But we want a large cache and a pipeline design at the same time, which means that you need to introduce a cache hierarchy. So this is the real reason why level 2 caches were introduced, actually, because level 1 caches are too tightly coupled with the pipeline design. They're really there to supply the instruction that's executing at that moment. As a result, you cannot make it large. There's actually another reason why we cannot make it large. It's tied to the virtual memory, and we'll talk about that. Or it's tied to a particular design of the virtual memory. Okay, so let's talk about manual versus automatic. Again, this is another trade-off where the programmer can go crazy, whereas microarchitect also can go crazy potentially. Let's see. So if you can punt the management of the cache to the programmer and say, programmer manages the data movement across these levels in the cache hierarchy. Their cache is exposed. This is usually called a scratchpad memory, which will come. But this is usually too painful for programmers on substantial programs. You need to be a really good programmer to be able to do this. And this was the case in the 1950s, core versus drum memory. Still done in some embedded processors. They're on-chip scratchpad SRAM as opposed to a cache. And GPUs, they not only have caches, they also have the scratchpad memory. For some reason, they call it shared memory. I really hate that word because it shouldn't be called shared memory. Do you agree with that? Shared memory has some other semantics. But it's really a scratchpad memory. GPUs have caches as well as scratchpad memory. Now the programmer needs to manage the scratchpad memory manually, and cache is managed automatically. And we'll talk about that. But basically, this is a hard task. If you do it automatically, now the hardware manages data movement across the levels. You add more complexity to the hardware, but the programmer's life is easier. Right? That's a big plus again over here. Remember, we always straddle the space between hardware and the software. The average programmer doesn't need to know about it. You don't need to know how big the cache is, how it works to write a correct program. And that's very important. In fact, automatically your program is faster because there's a cache compared to no cache, right? But what if you want a really fast program, then you probably want to know about that cache and the size of it such that you ensure that you don't overflow the size with your working set. And if you know the policies employed in the cache in terms of replacement, you can actually do better as a programmer, but then that complicates your life, right? Okay, so basically automatic management in memory hierarchy was envisioned by Maurice Wilkes. That's the paper. It's not required, but basically by a slave memory, I mean one which automatically accumulates to itself words that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of main memory access to be incurred again. But there are other papers. There's actually older papers on caching. And the oldest one that I know of that talks about this notion is by this Fotheringham from 1961. But these are harder to read. You're more than welcome to read it. If you want this paper, I can send it to you. It's not available online as far as I know. We found it in a library. That's another notion that's getting extinct. But in a library, but this is online. But these are harder to read. And these talk about a lot of other things than caching, whereas Maurice Wilkes' paper is focused on caching. So a modern memory hierarchy looks like this. Register file is also part of the memory hierarchy, actually. But it's really managed by the compiler. It's manual. If you have a scratch pad, actually, this dashed line actually goes over here because that's also managed manually. But in a general purpose processor, you have something like this. There's automatic hardware cache management. And at the end over here, there's another virtual to physical boundary, if you will. You have demand paging. When you run out of physical memory, automatically somebody manages that virtual to physical or demand paging part. So a little bit about latency analysis. Have you guys done this before? Some of it probably yes. Yeah? Okay, that's boring. I find this boring also, actually, so I'm going to go over this relatively quickly. But I think it's good to think about this. So for a given memory hierarchy level I can be 1, 2, 3, 4 over there. That memory hierarchy level, that cache, has a technology intrinsic access time, TI, that's the access latency, and there's a perceived access time, TI, that's longer than this little TI, because you can hit or miss at that level, right? So basically, you have a chance that you're going to hit, and then you're going to experience the access latency of this little TI, and there's a chance that you're going to miss, and then you're going to experience the access latency of this level, as well as the aggregate of all of the outer levels, right? And this is a hierarchical analysis. Well, hit rate plus miss rate should be 1. But this is hierarchical because of this, basically. The access latency of a level is the access latency of this level, intrinsic access latency of this level, and the probability that you're going to hit, plus the probability that you're going to miss, times the access latency of this level, plus the bigger access latency, perceived access time of the next level. That's this hierarchical analysis. I know it's too many words for something so simple, right? Basically, that's it. But you can analyze. Hit rate and miss rate are defined to be, well, HI and MI are defined to be hit rate and miss rate of just the references that missed at the previous level. So you get a recursive latency equation that looks like this by combining the TI, little ti over here, right? And you can actually now do some trade-offs. So the goal is to achieve desired perceived latency at the first level, which is L1 cache, within allowed cost. Ideally, you want the first level to have the access latency of that intrinsic access latency of that level. But this is not going to be easy to satisfy, right? You want to keep the miss rate low at each level. You want to keep the time to access the next level low also. So increasing capacity lowers the miss rate, but now it increases your intrinsic access latency, clearly. You can lower the miss rate by smarter management, and we're going to talk about that. What do you replace? What do you keep in the cache, basically? What do you anticipate? Can you anticipate the stuff that you should bring into the cache such that you're not going to experience the latency of it when you need it? That's called prefetching. And you can keep the next level access low by making them faster, but now it increases the cost. And you can introduce intermediate hierarchies to reduce the cost. So this is basically an optimization problem that can be defined. But I'll give you an example. Basically, this is Intel Pentium 4. It had a 3.6 gigahertz processor, which is irrelevant over here. But basically, it had these parameters for the L1 cache. The capacity is like this. The intrinsic latency is 4 cycles for integer fetches, because integers required smaller words, and FP required larger words. L2 access is 18 cycles, and main memory access is, let's say, 50 nanoseconds. So notice that best case latency is not 1. So because this is so high frequency, it takes 4 cycles to access the cache. And worst case access latencies are actually into 500 plus cycles. And that's the nature of things today. Memory latencies are very long because we know how to make computation fast. But making memory faster is a different issue. It's more costly. So let's take a look at some trade-offs. If your miss rate is 10% at the first level and 10% at the second level, the experienced access latency at the first level is 7.6 cycles. Right? You can do this calculation on your own with that hierarchical equation. If your miss rate is much lower, your experienced access latency is closer to the intrinsic access latency of level 1, as you can see, right, 4.2. If your miss rate is 5% in the first level, you get 5 over here. But if you're, let's take a look at over here. These two things have experienced access latencies that are very similar, right? Basically, you can get a similar access latency at the first level, 5 versus 5.08, by making the miss rate higher over here, but lower over here, versus lower over here and higher over here, right? But your two different programs can have very similar access latencies at that level, right? And as you can see, this is 50% miss rate. So at the outer level, you can have a much higher miss rate, but this is out of references that do not, out of not so many references, because your hit rate over here is 99%, right? Okay, there's nothing magic about this. You can play with the values. But I will hopefully convince you later that miss rate is not the only thing, because what this doesn't take into account is the parallelism of the misses. Basically, this says this is the latency experienced by an average access. But this is not necessarily correlating perfectly with what's the stall time that the processor experiences. Okay, any questions on this? No? That's good. Okay, so cache is generically any structure that memoizes frequently used results to avoid repeating the long latency operations required to reproduce the results from scratch. A web cache is a cache also. So there's actually web caches that are used. There are a lot of software caches. So, but we're going to talk about the hardware caches in this context, because software caches, you have a lot of freedom, right? You can design the cache. You can basically allocate a huge amount of memory, and then you can say, I'm going to manage this memory out of the disk, and I can replace blocks. I can have very different cache blocks. For example, I can cache pages. Some pages could be 4 kilobytes. Some pages can be 2 kilobytes. Some pages could be 1 byte, right? You have a different kind of problem there. But in the on-die context, you have an automatically managed memory hierarchy based on SRAM. And we memoize in SRAM the most frequently accessed. It's not clear if that's true, but we'll see. There are other potential things that you want to cache to avoid repeatedly paying for the DRAM access latency. So let me give you some terminology first, some of which you may be familiar with, but I want to use the terminology here. Block is the unit of storage in the cache. IBM uses line. I guess you could use either. But this is, people use line and block, and they're interchangeable, but that's because things have developed in different ways. That's historical reasons. And memory is logically divided into cache blocks that map to locations in the cache. On a reference, you can get a hit. You use the cache data instead of accessing the memory. You get a miss if the reference is not in the cache, and you bring the block into the cache. But even then, you have a choice. Maybe you have to kick something else to bring the block into the cache, right? Maybe you have enough space in that set at that moment. Or maybe you don't bring the block into the cache because something else that the things that you have are you think that you're going to use, right? So there are many important cache design decisions in the context of hardware caches. Placement. Where and how to place and find a block in the cache. Replacement, what data to remove to make room in the cache. Granularity of management, do you have large blocks, small blocks? Do you have sub-blocks? Have you guys learned about sub-block caches? No? Sector caches? Well, good, hopefully we'll get to it. Write policy, what do we do about writes? If you're doing a write, do you bring the block into the cache? Instructions versus data, do we treat them separately? So there's a huge set of design options here, some of which we will cover. But let's look at the abstraction over here. Basically, a hardware cache consists of a tag store and a data store, and you supply the address to it. The tag store answers the question, is the address in the cache? And it also has some bookkeeping information to enable some of these decisions, replacement, for example. Data store stores the memory blocks. Tag store gives you a hit or miss value, and if it's a hit, you use the data. If it's a miss, then you do something else. You access the next level. This is the cache hit rate, number of hits divided by number of hits plus misses, or number of hits divided by number of accesses. And average memory access time is a metric that people use to calculate cache efficiency, effectiveness. It gets the hit rate times hit latency plus miss rate times miss latency. Nothing magic here. But can reducing AMAT reduce performance? That's one aside we'll talk about. Does anybody have an idea about this? If you reduce the average memory access time, can it ever reduce performance? Not a trick question. No? Or people are tired right now? Maybe it is a trick question. So it makes sense to reduce average memory access time, right? Because that, you want to maximize your hit rate because hit latency is lower. But can it reduce your performance if you actually optimize for this? Let me make it simpler. Let's say I want to maximize my hit rate. Increasing your hit rate, can it reduce performance? Oh, I see. I mean, I'm not saying useless data. Yeah. You're still getting useful data. You have a higher hit rate.
No, we can probably use the other algorithm,
Yeah.
which is less efficient asymptotically,
Uh-huh.
but it's more friendly to cache. So we have more like cache hits, and it's like better for cache. It has
Yeah.
we reduce the average.
Memory access time. But then you're increasing your hit rate again, right, with that algorithm. Yes. So I'll give you an idea of this later on. We won't get to it today, but the answer is yes. You can, if you reduce the average memory access time, you can actually reduce performance. Because what this doesn't take into account is the cost of the cache misses, if you think about it. And we'll see that later on. Keep that thought. But let's talk about the basic hardware cache design in the remaining time. So we will start with a basic hardware cache design, which I'm going to go over relatively quickly. Then we will examine a multitude of ideas to make it better. So let's start with the basic. Memory is logically divided into fixed size blocks. I mean, again, you can even question this, right? Why fixed size? Fixed size because it's simple in hardware. If you're in software, fixed size may not be that hard. Variable size may not be that hard. Each block maps to a location in the cache determined by the index bits in the address. And this is used to index into the tag and data stores. So this is an example address, 8-bit address. Let's say you're storing, your block size is 2 to the 3, and this is byte addressable. So your block size is 8 bytes here, right? And in this case, you have 8 blocks, right? Or 8 sets, and your tag is this. So whenever you do a cache access, you first index into the tag and data stores that I've shown you earlier with the index bits. So you use these index bits and index into one of the 8 locations, right? And check the valid bit in the tag store and compare the tag bits in the address with the stored tag in the tag store. That's the idea. Does that make sense to everyone? Is it clear? You've seen this before, hopefully? Okay, that's why I'm going to go through this relatively quickly. If a block is in the cache, it's a cache hit, the stored tag should be valid and match the tag of the block, right? Again, that makes sense, hopefully. So let's look at a direct map cache. Actually, what I discussed here is kind of like a direct map cache. So in a direct map cache, you basically have only one location in the index that you can store the data for. So this is, let's look at, this is our memory. We have 256 bytes in the memory. This is a toy memory. 8-byte blocks, cache blocks. As a result, memory is kind of divided into 32 blocks over here, right? 32 different blocks. Ignore the green ones now. I'm not going to use the green ones for now. Assume we have a cache that has 64 bytes and 8 blocks. It basically, in a direct map cache, a block can go to only one location. So you have the tag store, valid bits, and the tag, and the data store. So you have 1, 2, 3, 4, 5, 6, 7, 8 blocks, right? And if you want to, there's the valid bit and the tag. And this is how you actually index this direct map cache. Again, this is 8-byte blocks. 8-byte blocks over here. That's why in a byte addressable address, you need 3 bits for specifying the byte and block. You index the cache using the index bits, which brings you to one of those 8 locations. And you check the tag, and you get the data if there is a valid bit match and a tag match, right? So how do you do the tag match? Basically, you get a hit logic if it's valid, and if the tag matches a tag over here for the address that you're accessing, you basically get the data. So there doesn't need to be a mux over here, actually, but that mux will be extend. So in this case, this mux is just a wire, right? Well, the mux is actually for the byte and block, sorry. So you may be accessing only 1 byte over here. So this mux is to mux out the byte that you want. Assume you want to access a single byte. But there will be another mux that we add later on. So in this case, it's direct mapped because one block in memory can go to only one location, right? And that location is where we index into. So if you look over here, this is block 0. This is block 8. This is block, is that true? 16. This is 24. Yeah, 0, 8, 16, 24. They all have the same index bits. They're all 0. Which means that these blocks can only be cached at location 0 over here. Make sense? Which means that the addresses that have the same index bits contend for the same location. And these 4 blocks, 4 pool blocks, contend for that location. If you're accessing only those 4 blocks and nothing else in memory, you're basically thrashing your cache because they all go to the same location, and you cannot keep all of the blocks in that one location, right? That's the downside of a direct map cache. You get conflict misses. This is called a conflict miss. These 4 things conflict with each other. Make sense? Okay, so how do we actually reduce the conflict misses? Well, okay, let me give you this one. Basically, this is what I said. 2 blocks in memory that map to the same index in the cache cannot be present in the cache at the same time because one index can store 1 entry. And you can get 0% hit rate if more than one block accessed more than one block is accessed in an interleaved manner that map to the same index. Let's give that example. Assume address A and B have the same index bits, address 0 and 8 in the previous example. 0, 8, 0, 8, 0, 8, 0, 8, 0, 8. You keep doing that. This is block address. You get conflict in all accesses, and all accesses are misses. You get 0% hit rate. That sounds bad. So people have developed set associativity. The idea is to reduce the impact of this sort of access pattern. Instead of having one column of 8, so if you look over here, in the tag store and data store, you have one column of 8 locations. You basically change the structure such that you have 2 columns of 4 blocks, like this. Basically, whenever you index, you can store 2 things at that index. This is called a set. So a set can contain 2 blocks. That's the idea. Your byte and block remains the same, but your index bits go away. You reduce it by 1 because now you have 4 possible places to index into, and now your tag needs to match. So if you look at the data store, you can store two things, but you need to store two tags also and val bits. Now you need to add two comparisons, because when you index, you don't know which one may match. And this hit logic becomes more complicated. And that hit logic decides if there is a match, which way you should get the data block from, right? Is it way 0 or way 1, right? So there's another mux that we've added. So it's more complicated to have a set associative cache. The key idea is within the set, you have multiple locations, multiple blocks that you can store. It's associative memory within the set. It's associative because you use a tag to distinguish. Index is not enough of a distinguisher. Indexes are the same, but the tag is used to distinguish between those two blocks. Accommodates conflicts better. Now, if you have an access pattern, A and B, addresses 0 and 8, well, they go to the same set, but now you can store them at the same time. A here, B here, you're golden, right? So you get better hit rate. The problem is you are more complex, slower access, larger tag store, right? Larger tag store because your tag size is large, as you can see. And also you have this replacement problem now, right? Previously you had only one thing to decide, are you going to kick it out of the cache? Now you have two things. Which one do you replace? Now this doesn't solve the problem if you have ABC, 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 right? So you can take it further, or addresses 0, 8, and 16. You have three things that you're accessing, ABC, 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 but you have only two slots. Well, how do you solve that? Make the cache higher associative. Have two indices, two sets, but have the ability to store 4 blocks in the set. Now your likelihood of conflicts is even lower, but then you have more tag comparators and wider data mux and larger tags. Now taken to the extreme, you have a fully associative cache. A block can be placed in any cache location. There's no index bits. This is fully associative or associative memory. Basically, you take the tag. There's no index bits. You have the tag and you have the byte and block. You basically compare the tag to all of the possible tag locations in the cache. And you have a lot of comparators as a result. And then you have a huge wide mux. Make sense? That's the idea of associativity. And that's the clear trade-off between associativity and hit rate. Now I'll ask you the question, does higher associativity always lead to lower hit rate? That's a trick question again. And the answer is no. Not surprisingly, but you can construct an example when higher associativity actually leads to the same hit rate, easy, but also lower hit rate depending on the access pattern and the replacement policy. But we're not going to talk about that right now. That could be a homework question, actually, if Juan reminds me of it. Or maybe you can now start thinking about it. You don't believe me, maybe. That's okay. Now you can prove it. Okay, this is the last slide I'll cover, I think. Basically, associativity leads to many trade-offs. Degree of associativity is how many blocks can map to the same index or set. Higher associativity gives you higher hit rate most of the time, but slower cache access time, hit latency, and data access latency, more expensive hardware, more comparators. And usually there is diminishing returns from higher associativity. Basically, the curve looks like this. Going from direct map to two-way associative buys you a lot in hit rate. This is averaged across a lot of programs. Of course, one program may not be affected at all, right? If you increase the associativity, you gain nothing. For example, random access patterns you gain nothing by increasing cache size even, right? But you get diminishing returns. If your associativity is 64, the relative benefit of going from 32 to 64 is lower. Okay, maybe this is a good place to stop, and then we can continue next time. Okay, see you next time. Wait for your homeworks.